whereas what is the extension of the gravitational influence of the halo? Can we actually even define a proper boundary of the halo? And depending on who you're talking to, you'll end up with a variety of definitions of where to draw that line which separates a halo from everything outside of it. And as you can see, so on the left panel here is a picture from a simulation of zoomed in on the dark matter, on a dark matter halo, and on the right is the density profile. And all these different radii, all these different locations are essentially what different people will refer to as the boundary of the halo. It's usually defined as the radius that sort of encompasses some constant times the background density of the universe. So it's an overdense region. And you define some m within some delta over density. And it can range actually a variety of scales even within the halo. And typically, now we know that all of these scales can actually be very sensitive to different kinds of physical processes that set up the entire, that lead to the setting up of the entire structure of the dark matter halo. So in work by Diemer and Kravtsov a few years back now, it was noticed while studying dark matter halos, by studying stacked dark matter profiles of halos in n-body simulations, that in a region, in the outer regions of the halo, which is close to the virial radius of the halo, typically thought to be the boundary of a halo, close to the virial radius, it was seen that if you look at the slope of the density profile, so on the bottom panel, we've plotted the slope of the density profile. On the right is distance from the center. For an NFW-like system, you would expect this dot dashed line where you'd be -1 near the center and go to -3 in the outskirts. But in a narrow localized region around the edges of, around the outskirts of the dark matter halo, it was seen that the density profile actually deviates quite significantly from what you expect from NFW. In fact, the slope of the profile, the steepness of the profile, can reach -3, -4, or even higher than that in some cases. Now, what was this feature that we were essentially seeing? Now, when we think, now when we essentially think of a halo, there is actually a very dynamical way of defining how to separate out different regions of the halo. So at the same time, we were also thinking about sorry, this is a bit slow. Yeah. So, right. So we were also at that point of time, thinking of the halo sort of in a different way. One way of really understanding the dynamical processes that shape a halo is to look at the phase space of halo evolution. Okay, so going off from the configuration space where we map a halo in as density as a function of distance, if we look at the orbits of particles inside dark matter halos in the phase space, where on the y-axis we are looking at the radial velocity of dark matter particles, and on the x-axis we are looking at distance from the halo center. In this space, actually, it's actually quite clear what happens near the boundary or near the so-called virial radius that we talk of about the halo. And in this space, actually, there's a very clear boundary, a very clear separation of a region where you find particles that are bound to the halo, that are orbiting the halo, versus particles that are just falling in for the first time. So if you look at the phase space of dark matter halos, on the y-axis over here, we have the radial velocity. So something that is moving out will have a positive radial velocity, and something that's moving in will have a negative radial velocity. So far outside the dark matter halo, things are just moving away with the Hubble flow, so it has a positive velocity. Whereas as you move closer and closer in to the dark matter halo, you reach a region of turnaround where it cuts off from the Hubble flow. And then you subsequently, you reach regions of particles which have more and more negative velocities, essentially falling into the potential, until you reach the center of the halo, where it basically just crosses over smoothly to a positive velocity, until it moves out in the halo potential in the outgoing part of its orbit, till it splashes back, or essentially turns around again when it reaches its first apocenter. Right? So it's at apocenter, so its radial velocity goes to 0, and it essentially turns around and does the same thing over and over again. Right? So this outermost apocenter of the most recently accreted material, so the material that has fallen into the potential very recently, essentially delineates a boundary between the multi-streaming region, or the virialized region, where at one location you have several velocities, which is why it's called multi-streaming, versus an infall region, where you just have particles falling into the halo for the first time. So this boundary essentially can separate, in phase space, essentially separates out two regions around the dark matter halo. Is there a way to change it through this? Does not seem to be working. Oh, I can just change it with my computer if that's. Thank you. So what we basically found is that, so what we basically can say is that the region around a dark matter halo is separated into three regions. One is the orbiting or the multi-streaming region, and then the infall region. And if you look at the phase space of dark matter halos, you can clearly delineate these regions. The density profile of a halo is essentially just the integral of the phase space in the radial velocity direction. And if you had a pure spherical, smooth and fall halo, you would get these really sharp caustics at each of these apocenters of particle orbits. But in a more realistic case, where you have a non-spherical halo, these caustics get washed out. But what we are essentially finding in the plot that I showed you earlier from the Dima-Kravtsov is that the outermost caustic, which essentially separates out the two regions, tends to still remain prominent, even when we take into account non-spherical halos, and in fact, even when we take into account stacked halos from simulation. So what we essentially saw is that on the top panel is a phase space from dark matter simulations, from an n-body simulations. This is stacked over plenty of halos. And this steepening of the density profile near the outskirts of a halo essentially corresponds to this boundary between the virialized or orbiting region from the infall region of the dark matter halo. And if you pick on particles closer to zero velocity, you actually can make this feature sharper. So this feature essentially is a remarkably consistent feature, even when you're stacking over several halos which have quite a bit of different evolution histories. This boundary actually stays quite prominent even when you sort of average over these evolution histories. So some of the important things that this boundary depends on, we found is primarily, of course, it depends on mass. The larger the halo, it dominates its environment, and to first order actually splashback this radius that we call splashback radius because it's at the location where particles are turning around. So it depends on the mass of the halo, and other than that, it has dependencies more strongly on the accretion rate of the halo. So how quickly the halo is growing. Essentially because it's tracking the apocenter. So if your potential is growing faster, at every orbit, the particle cannot go out far enough out, right? So if you increase the accretion rate of the halo, the first apocenter shrinks to a smaller and smaller radius with respect to this is in units of r over r vir. Sorry, the label is not there. So a faster accreting halo has a smaller splashback radius. It also depends on the redshift at which we are observing the halo, essentially because the overdensity at splashback, or in terms of R over R200m, depends also on the redshift at which we are observing the halo, simply because the background is expanding away faster at lower redshifts, and it tends to happen at a higher overdensity at lower redshifts. All right. So just to point out, this feature, this splashback feature, essentially should also be there in all collisionless components of the dark matter halo, apart from the dark matter particles themselves. So even galaxies and subhalos, substructure that fall into dark matter halos and orbit it, should also show this feature in their density profiles, this sharp cutoff. The only difference in subhalos or galaxies is that they're subject to tidal forces, which mostly affect the inner regions, and also dynamical friction, which will slow them down and push their splashback radius to smaller and smaller radius compared to the dark matter particles, and as a function of the subhalo mass. All right, so why is this feature interesting at all? To me, it's interesting because, of course, it gives a dynamical definition to the boundary of the halo. It gives us a physical definition of what mass is actually in bound orbits around dark matter halos. It also is a growth of, it's a probe of the growth history. Essentially, it's a fundamental length scale inside the dark matter. So if you have dark matter, you should, around at least the most massive halos, you should see this feature around it. So, and one of the most exciting things is that it's simple to understand physically, just because it's formed out of most recently accreted material that is not phase mixed, and the most exciting thing is that it's accessible observationally. So in subsequent work, we basically took this feature, and because the dynamics is set by basically gravitational collapse in an expanding universe, we relaxed all of these assumptions to see how the feature is affected in modified gravity models. So in particular, we found that modified gravity would affect orbits of subhalos and therefore push this, therefore have signatures on the subhalo splashback radius. We also looked at self-interacting dark matter and so on. So there's been a lot of work since then in the community to really map out these shells of apocenters around individual halos, in particular by Mansfield et al. And Deemer et al., who've been basically trying to track this problem in simulation and define these splashback shells for individual halos. So I won't go into the details of all of that, but I think one of the things that I want to cover is essentially the observations of this feature in actual galaxy clusters, work that has been really exciting to me to actually go out and measure this. And so the first, so in galaxy clusters, which are the most massive objects, we basically observe them in the distribution of galaxies, and we observe them. So we take the galaxies to trace the dark matter potential and measure their number density profile. And with that, we basically fit to find the splashback radius. And the other way we do it is using the lensing of background galaxies to actually measure the dark matter and its profile. So the first detection, actually, of the splashback radius feature was done in around 2016 by Moore et al., where they looked at optical clusters in SDSS. So these were the red mapper clusters in SDSS. So these were massive clusters expected to be more than 10 to the 14 solar masses. And they measured the splashback profile in the galaxy distribution for the first time, and it was clearly visible at the edges of the dark matter halos. In subsequent work, it was followed up there was more work that worked with the SDSS clusters and also in the DES galaxy survey. And for all of the optical clusters, one of the things that we were finding is that the measured splashback radius, my pointer's battery fell off. In any case, the measured splashback radius was actually smaller than by about 20% than what we expect from theoretical considerations, from n-body simulations. So on the top panel is the gray curve shows the galaxy distribution, and you can see the minimum, which corresponds to the splashback radius, is shifted to the left with respect to the theory curves, which are red and green. And also in weak lensing, we found a similar shift. It was less significant, but we found a similar shift to smaller radius. So while for a while that was puzzling, one of the it was known subsequently that optical clusters suffer quite dramatically from projection effects, and they tend to creep into our measurement of the splashback radius. So one of the things that we did following that was to go to SZ clusters, clusters that were selected by a different method using their SZ signal, and measured the feature in that in those clusters. So clusters selected using SZ cross galaxy. So when we look at SZ clusters, we actually find no significant inconsistencies with lambda CDM. The SZ clusters, so this is in SPT, and this was, these are SZ clusters selected using the SPT survey, and these are SZ clusters which were selected using the Planck survey, and this was SPT cross DES and Planck cross HSC. And we find that for at least clusters selected in SZ, there is no significant discrepancy between lambda CDM and what we are observing. So that was encouraging. So we can now go ahead and use this for several other things and try to pin down the measurement and see whether it agrees over a wide range of mass scales and so on. But one of the things that we did is from the, while the SPT survey had a small sample of clusters, through DES, through some work that I've been involved with DES, we also used galaxy clusters, SZ clusters selected using the ACT survey, where we have a much larger sample of SZ selected clusters. And we can use these clusters not only to measure the feature in galaxy distribution, but also in weak lensing. So weak lensing is a much harder measurement. So we need more statistics also to beat down the noise. So now using these ACT clusters, around 1,000 ACT cluster samples, we basically measure the splashback radius, which is shown in blue in the galaxy sample, and also in red using the lensing sample. So, and we found actually quite beautiful agreement in the location of the splashback feature in using lensing and using the galaxy distribution. It was also, I think, one of the few works that showed directly from observations for galaxy clusters that the galaxies and the dark matter actually quite closely follow each other, at least the bright galaxies and the dark matter quite closely follow each other down to very small radius, around 0.1 to a large radius. And there was and essentially it helps us really look at the halo in a different dynamical way. All right, so now that we have measurements from lensing and galaxy distributions, what can we use this feature for? What do we do with this feature? Of course, it's a very good tracer of mass. It's a very good tracer of accretion history. If we can find a way to divide our halos in accretion rate bins, we can try to measure the accretion rate. We can try to measure the correlation of this feature with accretion rate and try to measure the ages of halos, for example. But one of the things that I've been involved with is working to use this feature to study galaxy evolution in massive clusters. Essentially, our work and several other works have also been looking at the splashback radius as a function of galaxy color. So we have a massive cluster of halos and we have galaxies orbiting within them. And what happens to this feature if we split these galaxies based on the colors of the galaxies, which we expect trace the star formation rate of these galaxies. So essentially to study how galaxies evolved in these dense clustered environments. So one thing that we found is that for different colored galaxies, the distribution itself is quite different. And also the distribution of the slope profiles, so this is the density profile and this is the slope profile. The slope profile of galaxies around clusters of different colors are quite different from each other when you break them up into different galaxy bins. In particular, blue galaxies tend to show a really weak splashback feature, if at all. Red galaxies show a very sharp feature and it's pushed outside. And green galaxies have a feature which is weaker and sort of arguably pushed towards the center of the halo. So one of the ways that we thought that we could explain what we are observing is that the galaxies are, is that this movement of the minimum of the slope is essentially tracing the evolution of galaxies inside a cluster. So unlike dark matter particles, galaxies essentially evolve inside, as they orbit around the cluster. They don't stay constant. So a blue galaxy that enters will, and if there is intracluster processes that quench its star formation, a blue galaxy will eventually lose its star formation, quench its star formation, and turn into red galaxies. Now, what this means in terms of the phase space is that their phase space trajectories essentially cut off at different locations. So the multi-streaming region for a blue galaxy does not extend through the entire region of orbiting region of the halo, but stops somewhere after the first orbit. Whereas green galaxies go a little further, and maybe red, and by the time they reach the epicenter of their orbits, if they're quenched, we will not see any more blue or red galaxies beyond this point. So this essentially translates into their phase spaces being cut off from the infall, the multi-streaming being cut off from the single stream at different locations, creating this distribution of the minimum of the slope that depends on galaxy color. So we use this to essentially try to constrain how long red galaxies, blue and green galaxies have lived inside clusters, and we also used a simple exponential quenching model to essentially put constraints on the quenching timescales of these objects. So finally, I'll end with some basic reviews. So essentially, we are not only measuring, of course, the splashback region, we are measuring the entire distribution of matter and the entire distribution of galaxies inside of clusters, and we can really use the entire profile in the context of understanding where the boundary is and how it acts also like a timescale inside the halo to basically use it for various things that we want to learn about the evolution of dark matter particles and galaxies inside the halo. There's also been, so this picture I took from Rana et al., which is a very recent measurement of the splashback radius using a small sample of X-ray clusters from Rho Theta, and I think in future we'll have much more stronger measurements, but this is currently the current status of where the splashback radius measured from different observations stand with respect to what we expect from theory, and it's a nice compilation plot of where we are, and in future we'll essentially, with surveys like LSST and so on, we hope to narrow down this distribution. Finally, there's some recent work where, along with the dark matter, we're also measuring the gas distribution and trying to see how the edge of the gas distribution inside halos matches up with the edge of the dark matter halos, basically going towards sort of trying to get all the components of a cluster to understand the profile. So thank you. I'll stop here and leave the summary slides up, and hopefully I've been able to convince you that there's something interesting to see at the edge of dark matter halos, and you're free to think about how you want to use it. Thank you.
Thank you, Sushmita. We have time for a couple of questions.
Hi, very interesting work. Actually, I'm a little bit doubtful about, your underlying assumption is that dark matter halo, the same will be followed by the baryonic halo. But in shorter time scale, it may not be, because dark matter halos are cuspy, like it's non-interacting, so it's trained to be cuspy, whereas baryonic halos are like they are interacting. It will be it won't be as steeper as the dark matter halo. So how do you explain this? I mean, why you are expecting they will be following the same?
So if I understand your question correctly, you're saying that if you have baryons, it tends to make the inner regions of the halo.
No, because you are comparing it with SG observations. So SG comes from the electron density, not from dark matter density, obviously.
Yes, but SG. So one of the ways that we are using SZ is to select dark matter halos. So in the sense, we think that the SZ total YSZ signal traces the mass of the dark matter halos. So we select use the SZ signal to select in mass bins. And the other thing is, we expect the gas distribution to, particularly in galaxy clusters, the gas is expected to be in, not completely, but to some extent to be in hydrostatic equilibrium with the cluster. And we also expect the gas boundary to be in the region where the dark matter is confined. Actually, there are some simulations that show that that is not the case. Sometimes the gas boundary actually goes beyond it. Yeah. But we have not seen evidence from it from observations yet. And we also don't quite understand why the gas boundary is shifting beyond the edge of the dark matter region.
No, that is actually expected, because baryons are interacting. It's not. Dark matters are not.
Can we have the discussion later? Yeah. There are other people who want to ask questions. Yeah, Sandeep.
Yeah, thanks for the interesting talk. So I wanted to know what is the physical differences between the NFW and INST profile, which you discussed in earlier part of your talk. So like NFW and isothermal, they are differentiated with the feedback effect. So what physical processes lead to INST profile?
So both NFW and the INASTO profile are essentially profiles that have been used to fit what we observe in simulations. So it's not the origin of these profiles is not actually from like a theoretical motivation. It was seen that these NFW profiles and these INASTO profiles fit the halos better. The INASTO profiles has the freedom of having a much shallower slope in the inner regions, which you sometimes see in simulations. So that's why sometimes people will use an INASTO profile instead of an NFW profile in halos. But I think it's mostly a fitting function, and then people try to understand, theoretically where that comes from. Yeah, if anyone wants to add anything to that, please go ahead.
Yeah. Justin?
Yeah, over here. Sushmita, you talked about the splashback radius being used as a clock for galaxies, and
yes,
that blue galaxies essentially do not complete the full
yes,
cycle. Some of the observations from GASP as well as from observations of gas-rich galaxies in the Virgo cluster, they suggest that there are galaxies which are gas-rich and which are inside the contour which you kind of shaded in blue and green. And that's one of the puzzles as to how they manage to retain galaxies. Gas over there.
Yeah, no, that's a very interesting question. So I think it definitely depends on which galaxies you're looking at. Right. And in a way, you can use this framework to tell you how long a galaxy, if you could, for individual clusters it's harder, but right, if you have redshifts, you can sort of try to make the phase space directly, which people have done directly, and see where the blue galaxies or star-forming galaxies lie versus where other kind of galaxies lie. So on average, for these massive clusters, it seems like these bluer galaxies, the bluest galaxies, I should say, tend not to show a splashback-like feature where the rest, where you expect the particle splashback to be. So from that, we were inferring that maybe they've, quenched. But there can be populations of galaxies. And also, this is statistical. This is a stack. So there will be some fraction of galaxies that will stay, probably
so what
stay
I was
star-forming.
essentially trying to ask was,
Yeah.
has there been a study of what is the fraction of such galaxies which are in the inner regions and they are in the inner part of the phase plot?
Yeah.
It could be that the number is insignificant, but I have not seen any clear study of that. So I was just wondering if you're familiar with that.
Yeah, we can talk about that more. There is quite, even using SDSS and so on, there have been quite a bit of studies trying to sort of get the phase space, the line of sight projected phase space, and there also they see a difference, but maybe you're talking of a specific kind of galaxy, and I think it is interesting to actually divide on galaxy properties and see where they lie in that region. Yeah.
Okay, I'm sorry, we'll have to stop the discussions. It's been an interesting topic, but we have to move on. Thank you, Sushmita. So the next
Do you
talk
need
in
this?
this session is by Kai Lars Oster, and I assume it's related to machine learning.
Yeah, good morning, everyone, and many thanks to the organizers of asking me to present some research we do in Heidelberg. My name is Kai Polstra. I'm head of the Astroinformatics group at HITS, and we at HITS are very trans or interdisciplinary. Our groups are in many different fields. What connects us is not the field of research. What connects us are methods and methodology. And therefore, we have groups working on weather forecasting, natural language processing, but also groups working on astronomy. That's what I do. Oh, yeah, the screens are swapped. Give me a second. It was actually working when I tested. Where's my mouse pointer? Just checking. No, it's not the pointer. Now it's corrected. Sorry. Yeah, I didn't sleep well. I got fever last night. So, yeah, after on Wednesday in the workshop we had, and that was really well attended, I spoke about supervised machine learning. Often we have data, we have labels, and we train the machine to do a certain task. But sometimes that's not really feasible. So what do we do if we have too much data? Yeah, everyone says, let's use machine learning. But is really machine learning always the best tool to do? I tried to convince you that it has some advantages if used cleverly. So when talking about data, we have satellite missions like Gaia. And it's always that people talk about sizes. Yeah, it's a petabyte of data. And we have simulations as well. Yeah, that should be the illustrious simulation. And it's also something like a petabyte of data you have in there. And there, Volker Springel, a former group leader at HITS, was also involved in. And of course, we have huge instrumentation projects like the square kilometer array, where we talk about something like billions of gigabytes per night. Of course, this is raw data, and that means if you correlate it and get it to science-ready data, it reduces. But is it really about the size of the data? I had cases when I was working together with students who were working with some kind of Excel sheets. And if an Excel sheet has 65,000 rows and you go through them and you don't have a proper method to figure out which rows, which objects show a certain ratio of fluxes, you are lost. Already a megabyte of data can be too much. What we talk about is it's a complexity of the data in astronomy, and that's a nice and challenging thing actually astronomy offers. We have spatial structures, we have spectral structures, and we have temporal structures. So back then, I was getting involved in a project. And how is our brain working? Usually we try to simplify things by putting things into boxes. We want to classify things because it makes our life easier. We always want to have a certain schema of dealing with stuff. Very often, when we talk about morphologies of galaxies, we refer to the Hubble tuning fork as a scheme of classifying morphologies of galaxies. So back then, we used cheap humans. Any jump cannon was called Pickering's computers, and Any Jump Cannon did a great job. Back then, it was an unfair payment of female towards men that made female available for the job of manually analyzing 200,000 spectra, going through them one by one. And the good thing is, Annie Jump Cannon and her team were really clever. They learned that the classification schema is not as it was thought to be. They understand some physics, they understood some commonalities in the absorption and emission lines, and from that derived a new schema of how we talk about those kind of spectra of stars. So what about 50 million galaxies? So we now had the Sloan Digital Sky Survey and created 50 million galaxies. At that point, paying for a group of people to do the task of classification does not work anymore. So you think of gamification. We already heard some nice things by Ashish on, I always forget the name, what is the name? That, something for the real-time transients of Zwicky, a cool thing Do is doing, I don't see him at the moment. So really cool things we can do. We can communicate science and we can get labels, we can get classifications. Back then it was about classifying galaxies, morphologies of galaxies and seeing what they do. And citizen science evolved since then a lot. It's now in the humanities, it's looking at images and say, how many zebras do you see? Or what kind of jellyfish is visible on that image? A lot of funny tasks school kids already can work on. Back then, I got involved in a project called Radio Galaxy Zoo, and they asked me to assist with the analysis of the clicks the users did, a statistical analysis, and I sort of failed, and had problems with that. Because in Radio Galaxy Zoo, we are actually looking for these supermassive black holes that create jets, create radio galaxies, create nice morphological features. But now the clicking and corresponding the flux in the radio with some near-infrared flux is something different. So the search of eruptic black holes got me on the topic of morphologies. And the challenge in Radio Galaxy Zoo actually is to deal with a rotation and flipping invariance. And rotation and flipping invariance is something we very often actually have in our daily lives. So what does a scientist, an evil scientist from Germany do? You take human pattern recognition, or better, You take an untrained human brain, in this case it's Eva, my younger daughter. Back then she was really young and I was playing evil tricks on her. But that's how you start. You start with an untrained neural network to learn something. And given a specific task, and some of you might recall this task from times as kids, understanding about shapes and structures. And I gave her a very specific task to fit a certain piece at a certain location. So guess what happened? I told Eva, please put the brick in there. There's the schema, and she tried. And of course, it does not fit. Even though there are 3 quadratic structures, rectangular structures, and just 2 triangles on that shape, yeah, it does not fit. But I enforced her to put brute force on something to fit something in a classification schema that probably was not the right one. So at that point, I thought, okay, we now have the option of either having an expert inspecting every data item, or we could use machine learning to sort of not ask the scientific question directly, not to do supervised learning, not to train it to do a certain task, but to ask the computer to structure things by shape, to structure things by their structure, to sort them accordingly. And in the end, give this as a pre-calculation to the scientist. And then they can do their individual analysis based on commonalities in structures and shapes. So a very simple example are self-organizing maps. Here I'm showing you 3 simple forms: squares, ellipsoids, crosses, and triangles. And those ones are now representative for roughly 10,000 images, with noise, slightly rotated differently, so like it is in astronomy. And here the example is hilariously simple, you would say. Therefore, we just need a small self-organizing map. In this example, you see a latent space of 5 by 5 prototypes or latent coordinates, where you now take a new image you have, you try to figure out where it matches best on the map. That's shown here. So because it's empty, it just takes the first possible position. It tries to rotate it, and for each possible rotation, find the position that matches best. And then in the next step, it updates the map to get a little bit closer to the shape and the structure it has at hand. It's inspecting. So after one step, you see the first ellipsoid went there, the triangle went there, the square went there, now the cross went there. Everything starts to accumulate in one corner because there we have signal and we don't have signal anywhere. And now we accelerate the training a little bit, and you see it's spreading, it's self-organizing, it's learning how to puzzle those things around. It's like doing Eva was doing. She was turning the pieces and tried to fit it in, and this is now done very quickly. And giving it some time, and it's a simple task, the map evolves. And the map now allows me to understand, oh, I have something that looks like a square, I have something that looks like a cross, something that looks like an ellipsoid, and something that looks like a triangle. And of course, as I use for the updating something that connects over the latent space, I use a Gaussian distance function, so what is closer gets updated more, what is further away gets less updates. Thereby, I enforce that objects that are similar in the structural original space are placed next to each other. And now, instead of looking at 10,000 images, I look at 25 images. And it's exactly the concept on a GPU for brute force I now applied to Radio Galaxy Zoo. And when you run it on Radio Galaxy Zoo, and I used a hexagonal shape because then you have natural number distances, it has some advantages for calculation. You have 6 neighbors, not just 4, plus 4 with the square root of 2 distance. So some technicalities, and it looks cooler with a map evolves. And you see all the different shapes sort of get placed. And in the end, you now take this huge map we generated, and you start looking at the map, you start inspecting it, you try to understand what are the structures we find in our data set. And instead of going through roughly 200,000 objects manually, hand by hand, and asking people to say, this is a contour, this is how it belongs to each other, this is where the near-infrared flux is, you now start to annotate things. You say, okay, in the upper left corner, we have our double sources. Here, they are elongated, single compact ones. Those are weak or missing. Those are noisy images, separate. You can come up with your own names. You can come up with your own semantics to describe things. And if you're interested in different things, you can look for different structures. And you now can use this to transfer your annotation. So you used unsupervised learning to structure it. You inspect a small subset of the whole data. And you now can start transferring your annotations of your inspection to the individual items. Those heat maps now, blue is very similar, red is very unlikely. This one is in the lower left corner, so it's a single compact source. This one here is in the upper middle. Upper middle is a double. This one here is in the lower right, extended objects. Yeah, sort of correct. This one is in the upper left and upper middle, so I would call it a double and extended object. So by doing so, by coming up what you think should be the correct terms, and terms are completely different when you come to different fields in astronomy. We call things completely different. Halo we have for so many things, so this is a joint term for so many things in common. So we can do that. We can inspect it, annotate it, transfer the labels. And the next thing is we can look for outliers. If we plot in a histogram the distance of each image to its closest prototype, you see most objects have a small distance. That means they are well represented by the learned map. The learned map is covering the structural aspects of most sources. But then there's this heavy tail. Those are the sources that have a huge discrepancy between the closest prototype and themselves. So they are rare. They didn't have so much effect in training the map. And those are the ones I'm, as an expert, want to see. Those are the ones I really want to inspect because they tell me a lot of things. They are the extreme ones, the challenging ones, challenging for our physical models. So I had a master student working on that. So I had a master student and 4 GPUs in 6 months' time. Erica created a catalog of morphologies for roughly 1 million radio sources in FIRST, including their infrared counterparts from UKIDS. So she did so in 6 months, while we had 10,000 volunteers and roughly 4 postdocs over 4 years through Radio Galaxy Zoo, doing it for roughly 200,000 sources. Yes, and if you think of it, it is an excellent tool, Zooniverse, but it's excellent for the heavy tasks, for the complex tasks. We should give them the outliers. We should give them those things that are so hard to describe and someone wants to inspect, actually. Why do we give them the 60% of the sources that are boring dots? A boring dot, and clicking on it and say, yeah, it's a dot, is a boring task. So now this thing is used for LOFA, for example. Pink, it's called, the software. Raphael Mostert used it as a LOFA web tool. They use it to represent the shapes in LOFA. They use it for the SKA. We found, together with people from Perth, with Tim Galvin, we found some giant radio galaxies, so the sources that spread physically really over orders like a megaparsec, so really large sources. There a slice is. I wasn't sure that the slide is coming. So we really now use this technique to look for really elongated radio jets and look for those extreme sources, because the question here is, how can those large structures actually form given the time to evolve for the sources? And then it's helping to have a broader sample of sources that are widely elongated and huge. So back then I was involved or asked to give a talk at a conference on star formation history. I have no clue on star formation history. So I just know that the HR diagram tells me a little bit about, the ages and structure of stellar clusters. In that case, I thought, okay, let's do it now for the Magellanic Cloud, take stellar clusters from a catalog, transfer the HR diagram in a Hess plot, a number density plot that captures sort of the structure of the HR diagram for the individual sources. And then you do exactly the same thing. You train a self-organizing map. In this case, you just have to take into account the number of members of each individual cluster to get a comparable measure. And you can use it, like I showed in the video before, to train a map. And the map now learns structures from HR diagrams, abstract. Yeah, and it's not fitting isochrones, it's just learning roughly what are different shapes of HR diagrams. I don't have to put in any physics at the moment, I just let the software do its task and sort the data. So once it's done, the question is always, what is it good for? Absolutely nothing is what people would answer. But you can now check who's colorblind in the audience by putting color gradients on top. So we learn to project structures on a 2D plane. Now we encode those coordinates in the 2D plane, which itself sort of resemble the star formation history. Yeah, so we encode this and use green for the x-axis and red for the y-axis. And by doing so, we get a gradient that turns into yellow to the lower left. If you now put it on the LMC data, you see we have a lot of yellowish here at the front. And this is where star formation is actually happening by the LMC moving forward, creating a shock, and through that triggering star formation. So without putting any physics in, I can look at the data, I can look at the structures, I can do it really, really quickly, and I can start doing what I'm used to do. I can do an astrophysical interpretation and check those things. And then I can start fitting isochrones because my first hypothesis turned out to be correct, and now I can do the physics correctly. Time series analysis, another challenging thing. Here in this example, it's really hard to spot the difference of the different classes because our notion of time is sort of slightly different than our notion of space is. If we look at spatial structures, we understand things, but we don't understand in this temporal thing how things over a certain time are correlated with each other. We don't see those things intuitively because in the spatial representation it's not clearly visible. If you take those things and now put it in merely as a vector, you just plug in the individual measurements over time. In one of the standard algorithms, I don't know whether it was t-SNE here, but I think it was a t-distributed standard neighboring embedding. You see they separate, but they don't separate well. So it's the same concept. You take data from a high-dimensional space, you project it down, you want to preserve similarities in structures, but it does not work. Why doesn't it work? Because we didn't consider time as such. And time is something really, really important. What you need to do to take this temporal nature now into account is use recurrent neural network. The recurrent neural networks have a lot of backward connections inside that allow to memorize what happened in the past. And now you take a time series, you plug it in, you have your internal weights and biases, your internal states, and then you just learn in principle for those so-called echo state networks, you learn the output vector that connects all the hidden states to the output value. And in principle, you plug in y at t, and you want to get out y at t plus 1. If you now take those vectors that learn to sort of reconstruct a time series from the neural network, so you take the output vectors u, plug them in a simple architecture called autoencoder that has a part that compresses the data to a latent space, in this case a bottleneck of 2, and then reconstruct from that and tries to learn to reconstruct that. So you learn a neural network that represents your time. You plug the weights into an autoencoder, compress it, reconstruct it, and plug back the weights in. And now you measure how well you could reconstruct the time series. By doing so, and Nikos Giannotis, a postdoc of my group, did so, it turns out from merely a vector to something that is not agnostic of time, something that is aware of time, you are able to separate the classes very well. And you can start inspecting those things. We use similar approaches for Kepler data. Here you see a projection of pseudo-variables in Kepler data with exactly the same method, and we started to inspect them manually and found different kind of classes, we would say. What you now can do is you take your projection and you overplot physical properties. If you overplot metallicity, it seems the temporal structure, the temporal behavior, is not connected to metallicity. If you now look at temperature, it seems, oh, there seems to be a connection. If you look at surface gravity, it becomes even clearer. We didn't know why, but the referee pointed out, when Dennis Kugler, when we wrote that, the referee pointed out to us that this is something that just got discovered by another group. We were not aware of this particular literature, but that just got discovered, and they had to fit for several years in very intense calculation stuff we just discovered by chance with a very simple, straightforward approach. You can use this to start playing with spectra. A 2D plane, this is from a project we did together with ESO. Antonio Di Santo worked on that. You can have a 2D plane projecting spectra, in this case of HARPS. You can look at the reconstructions in real time. You can look at histogram and distribution. You connect it to all VO tools. You easily create, out of the concept of unsupervised dimensionality reduction techniques, you create a workflow that enables scientific discoveries. It's not going on. Because of the issue with the screen, it seems the video wants to play to its end. Yes. Sorry for that. I really don't know what's wrong. I manually switch the slide. That's always the safest thing to do. Because then I come to an end. So, if you now take a radio cube, radio data, it's a PPV plot, position, velocity. Each pixel is in principle a whole spectrum. If you just take the integral flux of the spectrum, the image looks like that. This is work I've done together with colleagues from Vienna. So you don't see anything except this is the Milky Way, I can tell you, on the left-hand side, and it's close to Orion. So if you now do exactly the same concept, you take all the spectra, you learn a self-organizing map, you train a self-organizing map, and you now have different kind of spectra represented here. You can use a nice color bar on top of that and use this to color your image. And immediately you start seeing the bubbly structure, the shells, the stuff they are interested in. You can use the discrepancy to understand the discrepancy between the prototypes and the actual spectra to understand where a lot of turbulence is happening, where the complex spectra are. So, and as I said, those things all combined together allows you to use projection, similarity search, because once you have such a latent space, you take a new image and say, give me all images that look alike, give me all spectra that look alike. It's really a good way to do things. You store things in a database, you can do things like individual annotation, create your own catalogs, you can do outlier detection, those you can put in the Zooniverse, and from the outliers you can create catalogs. So all the stuff we want to do actually with data. So let's come to the conclusion of unsupervised learning. Yeah, you saw what I did to Eva. I told her particularly put it in there. She's always complaining that I showed that video, but I think it's an important part of that message. Don't bias your system. Choose the right representation. As you have seen for the time, merely a vector does not work. Use a stupid but fast computer for the boring task of structuring all the data, so you as a scientist can do the creative interpretation of the task, of the data. So I don't know, some of you might have seen this image at ASI, and I now need some hand signs. ASI asked whether this is a penguin or a dolphin. Who is for a penguin? I need hand signs. Penguin? No hand signs. Who is for a dolphin? I'm a little bit upset. It seems the last 23 minutes you were not listening to me, because I think it's definitely a kingfisher. Don't get biased by putting things into boxes. And I actually found another nice kingfisher when I was preparing some updates on the slide. So with this, many thanks for your attention.
I have a question about your application of unsupervised learning to the star formation histories of star clusters. So as you know, star clusters are relatively simple systems. They have usually have what is called an SSP, a simple stellar population, which formed at the same time. Whereas galaxies have much more complex stellar populations. So have you tried applying the same technique to galaxies?
No. Because of this simple connection, and back then in astrophysics I was always doing some tutorials determining the age of a stellar cluster, because it's so simple by fitting some isochrones on the HR diagram. Yeah, I thought if I want to understand the star formation history of individual regions, it could be a good way to approach. I never tried to do that on a whole galaxy. No, of course not.
Okay.
Yeah.
So, but I can chat to you offline.
Oh yes, please.
In your experiments, have you tried reconstructing any of the astrophysical aggregate objects like stellar clusters or galaxy clusters backwards in time to find out from what initial conditions they were created?
Because it is not a temporal setting, no. But what we do a lot is try to make the projections physics informed, so that by projecting down, you could actually derive some isolines that tell you those are sources of similar age, those are sources of similar metallicity, things like that. But reconstructing things, no. There are so many fields of application is always the challenge, and we usually focus more on things on a cosmology scale.
Okay, just one more question. Did you find any mathematical relation between GPU speed and the number of objects that it should classify before implementing your model?
The point is, for a brute force approach, like the one with the rotation, the GPU implementation is so nice, because if you want to calculate something very similar for, let's say, a lot of different rotation and flipping states, it's always doing exactly the same calculation, but you have to do it very often. And that means you can do exactly the same calculation completely in parallel. And that's why this case I was talking about is so well performing when you switch to GPUs. And in principle, for most of the tasks, they are easily parallelizable, and therefore things run nicely on GPUs. Some tasks that are not so nice parallelizable definitely make it hard to do this porting. So if you think of some simulation codes, for example, then it's often very hard because you have to calculate forces between a lot of different elements and you have to do it all together, and doing things in parallel. The calculation of the forces, yes, but you have to aggregate things at a certain point, and there things break down at a certain amount.
I understand that. Sorry to interrupt you.
I think,
it's just that.
can we carry on this conversation
All right.
later?
Yeah, thank you.
Are there any other questions? Yeah, Indore.
How do you figure out the number of cells to provide in the final? How do you optimize it?
That's a very good question. So I always start with roughly square root of number of objects I have in the sample. But of course, the number of latent prototypes I need here is highly dependent on the complexity of the structure. So after you trained it and after you mapped something, you can look on how well are the sources represented by that. You can plot this histogram I had shown. And by doing so, you learn how well the individual structures are captured or not. If they are captured too well, you can decrease the number of prototypes. And if they are not well captured, you just increase it. There is no rule of thumb. As you have seen, if I would have put 100,000 images of the boxes, ellipsoids, triangles, and crosses in there, it would not change anything because it's very simplistic shapes.
Yeah, I think we're running out of time. So thank you, Kai, once again for the very interesting talk. We move on to the next talk, Come Closer Home. The next talk is by Anusha on the solar atmosphere.
Good morning, everyone. The title of my talk is Non-Equilibrium Effects in the Dynamic Solar Atmosphere. So first, I would like to thank the organizers for inviting me for this talk. So here in this image, you can see the different layers of the solar atmosphere: solar photosphere, chromosphere, corona, and the activities such as flares, etc. And the solar atmosphere temperature and density plot as a function of height can be seen in the right panel, which show that the density varies by nearly 12 orders of magnitude and temperature can vary from 1500 to 3000 where chemistry is important to millions of Kelvin where plasma is fully ionized. Therefore, the solar atmosphere itself can be considered as a laboratory. So, and also it is dynamic on the time scales from seconds to months, and in particular what we are interested is the solar chromosphere. Because there are several unresolved problems and we are interested particularly to understand the solar chromosphere because the chromosphere heating problem is something people have been trying to understand for several decades, and it connects the energy transfer from photosphere to the corona. So this is a movie of H alpha. A dynamic event is happening that you can see on the left, and within that red box a particular pixel corresponds to this time varying spectra of H alpha, and you can see so much of variation in this dynamic event. So now we would like to understand in particular the importance of radiation field, and it is timely to work on this exciting project of solar chromospheric research, because there will be new observations from SOOT on Aditya, which will give us chromospheric observations, and also there are new observations available from the world's largest solar telescope DCASE, and ever increasing computer power allows us to address the numerically challenging 3D radiative transfer simulations of the solar photosphere and the chromosphere. So now let us go to a particular part of the atmosphere, that is the solar chromosphere. Consider a dynamic event which is shown in the right panel here. This shows the image of the chromosphere which has fine structures called the fibrils, and also a dynamic event, this region bright event, that is showing a dynamic event. So now we want to understand this dynamics of the solar atmosphere, and in particular we are interested in understanding the role of radiation field in chromospheric heating. So such a modeling requires the solution of magnetohydrodynamic simulation, solution of magnetohydrodynamic equations to evolve physical quantities such as density, energy, velocity, etc. And on the other hand, we want radiative transfer equation to evolve populations which corresponds to the gas density and the constituents of the gas. And also we would like to understand or to get the radiation field which connects the magnetohydrodynamics and the radiative transfer equation. So as I mentioned before, what we want to know is how radiation field affects the atmospheric parameters such as temperature, pressure, etc. So this is a basic radiative transfer equation where you see I, which is the specific intensity, S is the source function, which is the ratio of emissivity to opacity, kappa is the total opacity, X is the frequency, R is the position vector, omega is the ray direction, and you can see that the equation here is the formal solution of this radiative transfer equation, which contains I don't think this pointer is working, only the slide changing is working. I hope you can see the first part of this equation which corresponds to the directly transmitted part, and the second part that couples the spatial which corresponds to the spatial coupling. So now this is a very nonlinear equation, and the solution is also nonlinear because the source function comes within this integral, and source function itself depends on the populations, which in turn depends on the radiation field through this term which we call mean intensity. I will come to the details of this. What I mean to say in this summary is that this is a nonlinear equation, so this is very difficult to solve. So the radiation field itself is a difficult part of the whole problem. That is particularly true because when the spatial scales over which the temperature changes are much larger than the mean free path of the particles, then you can assume something called as a local thermodynamic equilibrium, where the source function of this radiative transfer equation is just Planckian. It can be assumed in the high density solar photosphere, but as you go up in the low density chromosphere, this approximation of local thermodynamic equilibrium does not work anymore. In this case, the radiative transfer equation becomes a non-trivial, non-linear, non-LTE radiative transfer problem. And further, hydrogen is very important, and it is making up to 90% of the nuclei, and it is important because it often is a dominant electron donor, and it contains large part of the internal energy of the gas. Therefore, this excitation and ionization state of the hydrogen is also very important to understand. And if you are assuming local thermodynamic equilibrium, you can get the number densities in successive excited state by just simple Boltzmann equation, which has this form, and you can get the ionized number density in the successive ionization state by just Saha ionization equation. So, by just solving the Saha and the Boltzmann, you can get the number densities in all the levels of hydrogen, and you can just solve the transfer equation in just one step. So, there is it's a trivial problem when you are assuming local thermodynamic equilibrium. However, LTE is the thermodynamic equilibrium, local thermodynamic equilibrium approximation has a limited applicability. You can apply it to understanding photospheric spectral lines, for example, but in general, to compute the accretion numbers of bound and free state in a static atmosphere, we have to use what is called as a non-LTE statistical equilibrium or statistical steady state. Here, the driving term is this mean intensity, which is actually the integral of the specific intensity over all frequencies and angles. And further, this drives through the physical processes such as radiative absorption, stimulated emission, photoionization, and so on. So, for example, in this cartoon, many radiative processes and collisional processes are shown, which all become important and coupled if you want to properly take into account the scattering processes, etc. So, the rate system, the non-local thermodynamical rate system has this form now, where on the first term you can see the collisional rates, then the radiative rates, and all these processes balance with each other in the steady state approximation, so that you have a 0 right hand side. So, this will give us population in all the levels when you are not assuming local thermodynamic equilibrium, but you are in a static atmosphere without any dynamics. So, however, Klein and Knier demonstrated that this assumption of the kinetic equilibrium or the statistical equilibrium also breaks down in a dynamic atmosphere, because it produces contrasting ionization and recombination timescales. For example, from 1D simulations, it's shown that within the hot shock, it can be 50 seconds. The timescales of ionization and recombination can be as quick as 50 seconds, whereas in cool intershock regions, it can be as slow as 10 power 3 to 10 power 5 seconds. Therefore, the timescales on which these atomic populations reach their equilibrium with the environment is much more than the evolution timescales of the atmosphere. Therefore, there is no equilibrium reached. So, one has to take time dependence into account. So, in this case, the problem becomes even more general time dependent nonlinear radiative transfer problem. In this case, the rate system looks something like this here, with the collisional and the radiative rates similar to in the kinetic equilibrium approximation. But on the right, you do not have 0 anymore, but you have rate of change of populations and an advection term. So, there have been many attempts to solve this problem in order to model the solar chromosphere and solar atmosphere in general. The Radin code of Carlson and Stein solves 1D hydrodynamical equations of mass, momentum, and energy together with the non-equilibrium, non-LTE radiative transfer equation also. However, it is a hydro code and it is limited to 1D, and there is no magnetic field. So, it is not suitable for 3D radiative MHD simulations. And also they have some numerical issues which does not let the time step go higher. So, this is a limitation of this code. However, this has been extensively applied to many studies. Some studies are non-LTE radiating acoustic shocks in calcium K2V bright points, and to understand the hydrogen ionization in the dynamic atmosphere in this Carlson and Stein 2002 paper. And also it has been modified and applied to study flares, solar flares in from 2005 to even until now. People are using this code to understand the solar flares. So, then we have this Bifrost code which can do 2D and 3D non-equilibrium studies, I mean radiative MHD simulations with non-equilibrium effects, but they have done several approximations because otherwise it becomes very numerically complex. So, the approximations go in terms of neglecting time dependence in the rate system. So, equation of state and the radiative transfer calculations are very approximate, it is tabulated, and and so on, so that it can be done in 2D and 3D, but radiative transfer part is very approximate. And recently we have also been developing extension of the chromosphere for the code Muram code, which is a radiative MHD code, but here it is with a simplified radiative transfer similar to the Bifrost, which is presented in this paper. So even Bifrost has been applied to several studies, and some of the papers I have listed here where the Bifrost code is used for understanding non-equilibrium effects and to understand magnesium, formation of the magnesium lines and so on. Even then, even if they have applied this, it is not fully correct because of the underlying assumptions in the radiative transfer part. So what we are doing and what I have been doing for last few years is to develop a numerical method in the radiative transfer module for the state of the art MHD code Muram, such that it takes the time dependence of the rate system properly, and the non-equilibrium treatment of the molecular chemistry is also taken into account properly, so that the equation of state does not have a problem. And this is a numerically, it's a time implicit numerical scheme, and it is also suitable for 1D, 2D and 3D. So with these steps, the non-equilibrium method of the method that we have developed is presented in this paper here. And this development is generally in 3 steps. The first step is to develop the non-LTE, non-equilibrium radiative transfer solver and study this, test the steady state solutions. And then second stage is to determine the equation of state, and finally to apply it to the fully dynamical module, that is to interact with the magnetohydrodynamical module. So basically what we have done is a generalization to time of the short characteristic formal solution of the Cournot hour, and also the preconditioned multi-level approximate lambda iteration scheme of Rybicke and Hammer, and make the method implicit so that it allows large time steps. So in the steady state, we take the energy, density, velocity from the Muram, and then first do a formal solution and compute the collision and radiative rates, solve the rate matrix and iterate between these steps until convergence, and finally update the population. This is a steady state part. And we have verified our method by comparing with the equilibrium solutions computed from an independent core, and also we have compared with the chromospheric timescales computed in this Carlson and Stein. The second stage is to have the equation of state to determine temperature properly, and this is done by doing an energy balance. The kinetic energy and the internal energy should be balanced within a given time step. Balance not in general, but for that particular time step we take the energy from the magnetohydrodynamic part, and that energy should be equal to the total internal energy and the kinetic energy, so that we can, the internal energy changes because of the ionization and excitation, and accordingly temperature should change, and temperature determination is the important step here. And in this part we have also included the non-equilibrium rates of rate equations for hydrogen molecules of hydrogen H, H plus, H2, H2 plus and H minus. So this we solve together with the atomic rate system that is in the non-equilibrium rate system. And all other elements, we take total 14 elements, and everything else is either treated in local thermodynamic equilibrium, or we take proper collision rate, and only collision rate are considered for other elements. And coming to the stage 3, we have the here there is only hydrodynamical equations. So what we actually compute from the radiative transfer module and determine temperature, that will have an effect on the pressure, because we have to accumulate all the partial pressures from different constituent of the gas, and that goes into pressure in this momentum and energy equation. And another important number with all this complex solution of the radiative transfer equation is this flux divergence Q rad, which is shown in blue in this last energy equation here. And when Q is positive, it corresponds to heating, and when Q is negative, it corresponds to cooling. And Q is basically the negative of the flux divergence, where flux is defined here of the radiation, it is a radiative flux. So, these are the two numbers that we give from the radiative transfer part to the hydrodynamics part, and from hydrodynamics we get energy, density and velocity in the non-magnetic case. So, when we include magnetic field, there are additional magnetic heating terms in the momentum energy equation, and there is also an induction equation. So, now when we are in the fully dynamical case, so the same flow chart exists, but the loop now has changed because we have to iterate between the magnetohydrodynamics and the radiative part. So, for every solution of the magnetohydrodynamical solution, we solve the radiative transfer equation and the rate system and iterate the all three nonlinear systems until convergence, and finally update the population densities and the time steps. So, here is a movie of a temperature profile in the left. In the middle we have the hydrogen in ground state and ionized state and electrons. First panel is electrons, then the ground and the ionized state, and the last panel is the hydrogen molecules H2, H2 plus H minus. So, this is a 1.5 megameter chromosphere. It is not very high, but it is this is part is in work in progress. So, I have the evolution of hydrogen protons and neutrals and the molecules and the temperature. So, we have a reflective upper boundary here, and cooling is only, in general it should be through line and continuum formation. In this case I have only the continuum, and so you can see that this is the snapshot within the shock. You can see that the temperature profile is temperature profile and this, for example, the H2 here. So, they are inverted because when the temperature is cooler, there is more molecular formation, and when it is hot, you see that the ionization increases. So, what we see here is adiabatic cooling behind the shock and so on. So, in this particular solution or the simulation, we have a minimum temperature of 1500 Kelvin. So, this is a little bit higher, but I have only few seconds, like few seconds of the temperature and also the hydrogen atoms and the molecules. So, to summarize, we have developed a radiative transfer module which is now tested in 1D, but it is adaptable for 2D and 3D because it is developed in so that it can be in all 3 dimensions, and it is basically to simulate the solar chromosphere where strong cores of the strong lines such as calcium and magnesium are formed. And yeah, so the benchmarking of the equilibrium solutions has been done, and the importance of the molecular chemistry and the cooling rates is being done. And yes, the next step is to extend it to 2D and 3D, and also to make a 3D non-LTE non-equilibrium radiative transfer module, so that we can together with the magnetohydrodynamic core, so that we can simulate the structures and dynamics of the solar atmosphere and understand heating and cooling processes in more accurate form, because people have been doing a lot of approximations and still deriving the heating and cooling rates, etc. And also we can apply to understand the observations from Aditya, Iris, etc. And yeah, also to understand strong chromospheric H alpha line, the first image or the movie that I showed, to understand such time variation in the H alpha observations and things like that can be very interesting. And also these simulations can be used for forward modeling of spectropolarimetric observations. And yeah, you can also apply such code and improve other non-equilibrium applications to other astrophysical plasmas, maybe we can understand or learn from each other what we have got understood in what we have been doing to and interact with the other community. Yeah, thank you very much for your attention.
Thank you, Anusha. Questions? We have time for questions.
Anusha, you mentioned you're the upper reflecting boundary condition?
I mean, sometimes upper, but also open, like outflows also we consider
that
as.
may not be very realistic.
Yeah, definitely. So now in the upper, the second movie that I showed, it is the open outflows in the upper boundary. Yeah.
Okay. The other comment is how well the opacity effects are included, because
opacity is basically we don't improve it as such at the moment, but line opacity is of course, but the continuum opacity is taken as a table itself. Temperature, pressure table.
Talking about magnesium, calcium, all of them have.
Yeah, but lines are mostly, first we focus on the lines, but of course that is also important that has a secondary, that has a secondary, that we take up as a secondary step to improve the opacity. Continuum opacity is also not just use the tables, but I mean I have also a module that actually calculates the continuum opacities also, but it is very slow at the moment. So for test purposes, first we start with assuming that continuum opacities are just tabulated, but of course because anyway it will be updated for like through temperature effects, yes, but just that opacities themselves are assumed to be not fully coupled. Yeah.
Anusha? Yeah. Nice talk. I just have a more technical question. You mentioned about the implicit time stepping that you use, but have you actually thought about how the chemical reactions are getting converged with your implicit time stepping? Definitely
the chemistry is taken as every chemical reaction you have a new rate system. It is exactly the same as when you have like d and dt equal to the collision and radiative rates. Accordingly, I have d and dt for where n is a molecule. I have the formation minus the dissociation depending on the sign. So formation and dissociation rates are taken into account. It becomes a time dependent rate equation, and together with the other ionization and every excitation, I also solve the chemistry.
So the what is implicit? What is time implicit? The chemistry or the fluid?
Everything is implicit because we do iteration. Like every nonlinear system is solved in a given time step. So first you do the hydrodynamic, then you do the formal solution, then you do the rate system, and then iterate everything. So everything is implicit in this sense. So there is no, like earlier in all this Bifrost or the Muram that we have been doing on the approximate part, the hydrodynamic is solved only once, and then you take that is done, and then you solve the radiative transfer, maybe iterate between rate and, I mean they don't do full radiative transfer, so there is not much iteration.
So in this case I just would be interested to see the error, what sort of order accuracy you get in your code. That would be an interesting plot to see at some stage.
Yeah, maybe I will include that in.
Thank you.
Yeah. I mean in terms of approximation to LTE to this, people have already found with the Bifrost or the other Muram simulation that the departure from LTE is 10 power 3, 10 power 6, 10 power 9, it can be very high. So approximation of LTE is really not working. I mean it doesn't work in the chromosphere.
Yeah, hi. So actually I was looking for...
Where I am hearing?
Yeah, this is Sakshi.
Okay. Yeah.
So actually I was looking for a code that couples radiative transfer and MHD, and it was great to listen to you. So I was wondering, since you have explored the solar atmosphere, is it also possible to do the analysis of planetary atmosphere things with this code, considering MHD effects in consideration?
Yeah, in principle it should be possible, but depending on the composition, what you want to understand, and also there could be some different boundary conditions, and all these should be explored. Yeah, but in principle there should be no problem for the code itself. It's quite general.
Anusha,
yeah,
I was wondering that you have not shown any observations and how synthesis matches with the observations, say chromospheric lines of.
Yes, because this is still a work in progress, so we have not gone until that step that we compare with. Of course, for what people have been doing is compare the spectra. Like you take a particular spectra and then use these simulations and then a snapshot of the simulation as an atmosphere, use forward modeling to compare with the observations. But our aim is here to actually follow a shock, and actually even when there is a shock, people have not been able to simulate it properly because the adiabatic cooling makes the temperature go lower and lower, and they have an ad hoc limit that if it goes below 2000, you just assume that it won't go below 2000. It's like such kind of approximations are done in Bifrost or in the Muram also in the approximate. So, the first part is to properly don't do such any ad hoc approximations and try to include the molecular formation or something properly, so that we can resolve a shock. That is the major aim here. And once we have a simulation that can run for half an hour of the dynamic solar atmosphere, in which can go up to like 3 megameter, 6 megameter, then you can actually take these lines into account and understand the evolution observation that I showed in the first, that it was a H alpha observation, how dynamic it is. So, that can be compared, but may not be one to one, because then we have to simulate the whole flare in 3D. Then only we will be able to do. So, yeah, it is a long time to go, but yes, that is the aim eventually.
Thank you.
Okay, looks like there are no further questions. Thank you, Anusha, for your talk. So from the sun, we move to neutron stars. The next talk is by Debarati, and she'll be talking on probing the ultra-dense matter in neutron stars using gravitational waves.
Okay. This is a pointer, you can check it. Pointer.
Is it working?
Yeah. This one. Okay. Read this one. All right. I hope you can hear me. Okay. So first of all, let me start by thanking the organizers of this meeting to invite me to give this talk. And so this is my first ASI meeting. It's a pleasure to be here. Thanks to also the local organizers for having us here at IIT Indore. So my name is Debarati Chatterjee. I am associate professor at IUCA in Pune in India.
And I'm also chair of the upcoming mega science project called LIGO India. So I will be talking about it towards the end of my talk. So today I will present to you a very different field which has recently emerged, a very exciting field of gravitational wave science, and how it is helping us complement what we have been observing so far with conventional astronomy. So we will see how it helps us also to probe ultra-dense matter with neutron stars. So of course, we know that the story of neutron stars begins with the discovery of pulsars by this young lady, Jocelyn Bell. So at that time, it was not understood what is the source of these pulsations. Later, we know that these are related to neutron stars. So neutron stars, I'm talking about these compact objects that are left behind at the endpoint of evolution of massive stars that end in type 2 supernova explosions or core collapse supernova explosions. And a small back of the envelope calculation will tell you that these objects have masses comparable to that of the sun, but within a very small radius of only 10 kilometers. So imagine crushing the sun to 10 kilometers, and we can understand how high the densities in such systems can be. So these can exceed 2 to 10 times that of the densities we encounter in nuclei or nuclear experiments. And also these systems can have very low temperatures, magnetic fields that are extremely high, so ultra strong magnetic fields. So these systems motivate us to study extreme physics that we cannot do otherwise. So usually when we want to study fundamental physics, we use information from nuclear experiments, from hypernuclear experiments, heavy ion collision experiments in particle accelerators. But so here you can see that these systems ideally, so they go from 2 times, so nuclear experiments are close to nuclear saturation density. Heavy ion experiments can go at most up to 3 times saturation density. But neutron stars can exceed these densities, and they allow us to study fundamental physics that is not possible with the best of experimental facilities we have today. So again, giving you a diagrammatic representation of what I just told you. So we have some information coming from nuclear theory. So there have been recent developments in nuclear theory, in nuclear experiments, which give us information around this part of what we call the QCD phase diagram, that the quantum chromodynamics that tells us about strong interactions. So, so this is basically temperature as a function of density. And so we have some recent developments in these fields which give us information on nuclear theory and experiments, some developments in hypernuclear experiments. Heavy ion collisions here lie in this part of the diagram, which is for finite temperature and finite densities. And also there have been many recent developments of lattice QCD, which is at the high temperature, low density part of this diagram. But let me convince you that compact stars actually give us complementary information to all these developments I'm talking about. And the reason is that compact stars lie at along the low temperature and high density part of this figure. And also the other important thing is that these experiments I'm talking about are all for systems which have number of neutrons comparable to that of protons. Whereas compact stars, the number of neutrons are much larger. So neutron stars are primarily made of neutrons. So this is also another uncertainty in the kind of experiments that we have, so the terrestrial experiments that we have today. So all these complexities go into our theoretical models, because we have many different observations that I will come to in a couple of slides. But whatever we learned about from these recent developments, from nuclear theory and experiments, as well as heavy ion collision experiments, they tell us that neutron stars actually have a very complicated, a very complex internal structure. So while our knowledge of neutron stars is limited to nuclei, which are only in the outer part of neutron stars, so what we call the outer core. But as we go towards the center, the densities rapidly increase, going from nuclear density to several times, up to 10 times saturation density, and we actually have no idea what is happening there. So although we understand that probably there are some strange particles which appear in particle accelerators at such extreme conditions, these are conjectured to appear in the neutron star interior. The challenge is then to try and understand how to relate what is happening in the interior of neutron stars and try to find signatures in some observable, in some astrophysical observables. So this is what we do for theoretical modeling with the help of the equation of state. So as we know, equation of state is something that relates the pressure to the density for such low temperature systems. And so if we can relate the internal composition with the equation of state, then we can try to interpret what is there in the interior. From the equation of state, one can construct with the help of hydrodynamic equilibrium equations what is the global structure, for example, its mass or its radius, something that we can observe at different wavelengths, and then we can try to backtrace and find those signatures of the kind of matter we think appears under these extreme conditions. So here is a representative figure that shows you many such different nuclear models which correspond to different equations of state, and these can be translated or mapped onto a mass radius figure, something that we can observe, and then we can impose some kind of constraints. For example, the most massive neutron star observed would give us a limit onto which of these equations of state can explain such observations. So, for example, just to give you an idea, if you have this strange matter that is seen for a very brief time in particle accelerators, if they appear in the core of a neutron star, then that would typically suggest that the equation of state is soft, which means it is not as steep as it would be if you had only nucleons, and that would translate to the information that the masses of neutron stars would not be very high, and they would not be able to explain very massive neutron star observations. So neutron stars have been observed throughout the electromagnetic spectrum. So many of you have been working on multi-wavelength observations of neutron stars, and as we know that, so this gives us different kind of complementary information about its structure properties, like its mass, radius, or other properties, like for example, the spectra. From the spectra, if we can determine the gravitational redshift, that can also tell us about the compactness, which is related again with the mass and radius. So all these observations have been giving us information about neutron stars, but these were also associated with uncertainties. So many of these observations cannot distinguish between the complexities of the equation of state models that I was showing in the previous figure. So just to give you an example, if we can, so neutron stars are very dense systems, they are extremely relativistic. So if we can measure, in certain systems we can actually measure the post-Keplerian parameters. They tell us about, very accurately we can deduce the masses from such systems. So for all neutron stars in binary, here is a compilation of the masses that were measured, and So typically these large neutron star masses can give us some information about which are the equations of state that can actually explain such observations. So determining the neutron star radius is more difficult. Probably many of the astronomers here will know about this better than I do. So there have been many techniques that were used to determine the neutron star radius. So some of these are, say, thermonuclear X-ray bursts, burst oscillations, kilohertz QPOs, quasi-periodic oscillations, thermal spectra of cooling neutron stars, and so on. So all these different observations gave us some limits on the neutron star radius, but these were not very precise. Recently, there has been a mission launched by NASA called the NICER mission. So it's the Neutron Star Interior Composition Explorer. So the NICER mission uses a very different technique called the pulse profile modeling, and it has been able to put very important constraints on the neutron star mass and radius. So there have been observations of a couple of systems which have put very tight bounds on the mass and radius that helps us to constrain the neutron star equation of state, and therefore to understand what is there in the neutron star interior. The most recent breakthrough in this field came with the observation of gravitational waves. And the reason is that neutron stars, we know that back in 1915, Einstein proposed the theory of general relativity. And one of the predictions of this theory is that neutron stars, or black holes, so the systems which are extremely relativistic, extremely dense, they would distort matter, space-time around them. And if there are any perturbations in these systems, that would generate, they would set off gravitational waves. So if we can detect such gravitational waves, that would actually contain information coming from the interior of such systems. So, so neutron stars are very very important gravitational wave sources, because there can be many different phenomena that can give rise to gravitational wave emission. For example, if there are glitches in neutron stars, so glitches are something that are typically related with superfluidity in its interior. So for certain reason, if there is a rotational glitch, which means that a neutron star was, they are very accurate rotators, so they are one among the very accurate clocks in the universe. So if it happens that neutron stars, suddenly they change their rotational frequency, and so such glitches could set off burst gravitational waves. If there are flares, so neutron stars can be ultramagnetized. There can also be certain subclass of neutron stars called magnetars, which have extremely high magnetic fields. So these could also have, like analogous to solar flares, they could also have flares and outbursts, and these could also set off gravitational waves. There are also any other forms, like for example, if there is some kind of distortion, say a mountain on a neutron star would be a few centimeters, but it would still be a mountain. If there are distorted neutron stars because of magnetic fields, so these magnetars I was talking about would not be spherically shaped, but the extremely strong magnetic field would make them ellipsoidal shape, and that could also, when rotating, that could also be a source of continuous gravitational waves. So any kind of, basically any kind of non-axis symmetric perturbation in such systems could generate gravitational waves. So, and again, all of these properties are related with their internal structure. So, there, of course, have been many attempts to observe gravitational waves. The first indirect detection happened when Joseph Taylor and Russell Hulse observed a binary system of neutron stars, which are now called the Hulse-Taylor pulsar. And they showed that the trajectory of these systems, which are merging, so this exactly follows the prediction of general relativity. And so this confirmed Einstein's theory that gravitational waves would be emitted by such binary systems. And Taylor and Hulse obtained the Nobel Prize because of this discovery, and also because they established that gravitational waves exist, although this was an indirect detection. But of course, this motivated people to search for gravitational waves. There were many different types of observatories that were proposed. So these are some of these underground gravitational wave detectors, which are based on the interferometric technique, where you have a 4 kilometer long arm in which a laser source emits laser beams along 2 paths which are perpendicular to each other, and these would be reflected back, and if there is any gravitational wave passing through such a system, then this would give rise to a signal. So here you can see the LIGO detectors, so the Laser Interferometric Gravitational Wave Observatory, so in Hanford and Livingston, and the Virgo detector, which is at the border of France and Italy. So these, and of course there were some other detectors like GEO in Germany and TAMA in Japan. So all of them were looking for these gravitational wave sources in different bands from different astrophysical sources. Compact stars, I don't know if you can see it here. So compact stars actually lie in this part of the detection band that these observatories look for. And surely you can't see the axis here. So the strain for gravitational waves would be 10 to the power minus 24. So you can imagine how difficult it would be to detect this kind of gravitational waves. And of course, it took, the search was on for 100 years, but with a rapid increase in technologies, rapid development in technologies, the sensitivity got better and better. So from LIGO to advanced LIGO, and you can see advanced LIGO was already in the band of detection of these compact objects. So, of course, we already know that 2015, and the announcement came in 2016 of the first direct detection of gravitational waves from a binary system of black holes. So, this is the reason why Barry Barish, Rainer Weiss, and Kip Thorne were awarded the Nobel Prize in 2017. And so this motivated people to look for other sources like binary neutron star sources, and the first detection was a big surprise. So the GW 170817 was not only observed in gravitational waves, but also throughout the electromagnetic spectrum. And so this is what is considered to be the beginning of the era of multi-messenger astronomy, because the complementary detection of the electromagnetic counterparts of this event gave us information about many different models that were associated with binary neutron stars, but this was not confirmed until this discovery. For example, the gamma ray observations told us that binary neutron stars are associated with short gamma ray bursts. We know that there were observations of the kilonova, so this was also confirmed with this same event. So since then, since the first discovery, we have had, so this is the last gravitational wave catalog that was published at the end of the third observing run. And as we know that many sources were discovered, out of which, the light blue ones, so it's not very visible in this figure. So the light blue ones, so there are around 12 such observations. So I will show you very briefly what are some of these objects. They were not as surprising as the GW 170817, because these discoveries could not detect electromagnetic counterparts, but still they gave us a lot of very interesting information. For example, for this system, 190425, the masses that were the mass of the primary neutron star that was deduced was thought to be the heaviest binary neutron star. And so this, of course, that was a big challenge for the theoretical models to be able to explain such a large mass. The other important discovery came so this was the GW 190814. And for this observation, again, so the masses, so you can see here, so this was around 2.6 solar mass. And again, there was a big speculation as to whether it's a neutron star or a black hole. So you can see there are now more and more observations that are taking us by surprise, because of course we wanted to detect the most massive neutron star that puts a limit on equation of state models, but already we are reaching the frontier where the barrier, the mass gap between neutron stars and black holes is getting shorter. So, so this is sparking a debate as to whether such objects would be a black hole or a neutron star. There were also a couple of observations, couple of detections for the first hybrid stellar collision. So that means it's a system between a neutron star and a black hole. So this also put very interesting limits on on the model, on the neutron star theoretical models. So so this is the plot of so a summary plot for the detections of both electromagnetic and gravitational wave sources that correspond to the last observed catalog from the LIGO-Virgo collaboration. So at the bottom you can see all the neutron stars that were detected in electromagnetic. So these light yellow ones are the ones which were detected in multi-wavelength electromagnetic observations, and the orange ones are the ones which were detected in gravitational waves. So you can see here that we are already in a very interesting regime where the masses between, so earlier we thought that there is a mass gap between neutron stars and black holes. As you can see, we have already detected many systems which are within the mass gap, and now therefore these are raising a lot of interesting questions as to whether the theoretical models can put important constraints for these kind of objects. Finally, I would like to tell a little bit about how gravitational wave observations are helping us put constraints on the neutron star radius. I already told you that between the different observables, the mass is better constrained from binary systems, whereas neutron star radii, which were usually observed from isolated sources, they had large uncertainties, which is why there were many models which could simultaneously explain the same kind of observations, and we could not resolve between the different models and put a constraint on the equation of state. But now, thanks to gravitational wave observations, we can put constraints on the neutron star radius with the help of different kind of gravitational wave observations. For example, so in the in-spiral phase, when the neutron stars are spiraling in towards each other during the merger. So in the in-spiral phase, there could be tidal effects, and these effects show up in the gravitational waveform. So these have been detected and put very important constraints on the radius. We also expect that in the post-merger phase, so after the merger, there is a phase where the neutron stars collide, so they merge and then they form a metastable object which could promptly collapse to a black hole, or it could be an object that lives longer as a neutron star, and it all depends on the underlying equation of state. So there are now searches to detect so this is actually a multi-messenger effort because we can observe the signals in the multi-wavelength electromagnetic observations of this post-merger remnant, and until now we have not been able to detect the gravitational waves from the post-merger phase, but there are different proposals in line for other detectors in future that should be able to detect the gravitational waves coming from oscillations of this post-merger remnant. Also for isolated neutron stars, as I mentioned, such perturbations could be generated. So this is something that is already very well established in solar physics or in stellar physics. But so in addition to the different kinds of oscillations that are seen in solar heliosysmology or stellar seismology, we have already seen such kind of quasi-normal modes. These are well known in such systems. In addition, compact stars, neutron stars can also have pure space-time modes. So if any of these say the frequency or the damping time scale is observed for such systems, then we can also try to put a constraint on the radius from that. And of course, we have until now detected a pair of systems which were hybrid, so a neutron star binary, neutron star black hole binary, and the tidal disruption in such systems could also give us information about its radius. So, so this is depiction in numerical simulations. So numerical simulations help us to understand what is going on in such systems. So you can see here that if there are neutron stars in binary, so during the in-spiral phase, it is expected that the neutron stars would tidally deform each other, and that tidal deformation actually depends on parameters that are related to the global structure of the neutron star. And like I said, if we know the mass and radius, then we can put a constraint on the equation of state. So the LIGO-Virgo collaboration published important analysis of the GW170817 event, and so this told us that the neutron stars with softer equation of state were preferred than the stiffer ones. So this is very interesting for the theoretical community because it gives us information as to which equations of state would be compatible with such observations. So here are some of these studies which were published. And these analyses considered a large number of different equations of state. So all these equations of state are actually compatible with a set of nuclear experiments or hypernuclear experiments. And so as you can see that observations, so these kind of observations, for example, this limit that came from this event can help us to understand which of these models would actually be supported by this kind of observation. So again, looking ahead in the future, if we can have measurements of the neutron star mass and tidal deformability, then this would help put even more strict constraints on the neutron star equation of state. And so here you can see a plot where a certain region of the mass and radius would be excluded by the analysis of this event. And yeah, in addition to what we have from the electromagnetic observations. Another very interesting probability to constrain neutron star radius is from what I just told you, from the different oscillation modes of neutron stars. So if we can relate, if we can find some kind of universal relations that relate the properties of the neutron star, for example, its density, compactness, moment of inertia, then we could also derive some kind of relation with the frequency or with certain other observable features like the neutron star's moment of inertia, quadrupole moment, and so on. And so this is something that within my group we have been investigating in great detail. And just to mention that if we combine these gravitational wave observations with other observation, for example, the kilonova and the NICER observation I talked about, so these, with the help of Bayesian studies, they can put very interesting constraints on the mass and the radius. Finally, another very important aspect has come up in the recent times, and that is to combine multi-physics constraints at different densities. For example, if we can combine heavy ion collision experiment information, nuclear theory, for example, the chiral effective field theory, or perturbative QCD, then we can also try to constrain the equation of state better with the help of such multi-physics studies. I'm not sure what happened. Yeah, I think it.
How many more slides?
Probably, yeah.
Does this have battery?
No, it doesn't need battery. Yeah, sorry, I think I will need a second to. Yeah, it's rebooting.
Maybe we can, we're running out of time, so we can move on to the discussions.
I just had a couple of slides to show.
Sorry, no, I mean, we have really gone past the time, so I'm sorry about that. Any questions? A couple of questions? Yeah, please go ahead.
Yeah, I was intrigued by your statement that all the gravitational wave detections so far favor a soft neutron star equation of state. To what extent are the current generation of gravitational wave detectors sensitive to systems in which the neutron star equation of state would have been harder? Because a lot seems to depend upon the mass of the neutron star as well, especially if you account for the presence of magnetic fields within the core as well as outside it.
Yeah, so far electromagnetic observations have favored stiff equations of state.
Precisely.
Yeah, so exactly this is the reason why now, so we have two complementary events, two complementary observations that narrow down the region, because if you, I mean, the only thing is that we have very little observation. We have only one system, which is the GW170817, which is giving us the indication that this is soft. There have also been some heavy ion collision studies which indicate the equation of state is soft. So yeah, I mean, together they give us an important constraint on the equations of state that are compatible with both. Although now with the upcoming missions like the Einstein telescope or Cosmic Explorer and so on, so we expect to observe many such systems, and hopefully we'll observe many more with electromagnetic counterparts, and also many more which give us information about tidal deformability, from which we can confirm the observation from GW170817. Sure.
Yadesh.
Or oscillation modes,
yeah.
What kind of radiation signature would that ever give, if at all?
What kind of radio signature?
Yeah.
So,
would one see a radio observer? Would they see any
from the
imprint
quasi-normal
of this,
modes?
Yeah.
Yeah, I was talking mainly about the non-axial perturbations with set of gravitational waves. Well, yeah, I'll have to think about this. I mean, yeah, I'm not sure if I can.
Yeah, would it lead to some change in the
It depends on which
the
phenomenon generates it. So like I said, these quasi-normal modes could be active, for example, in the post-merger remnant. So that would have electromagnetic counterparts.
No, I was talking of normal neutron star and
Isolated. Yeah. So yeah, again, so if there are quasi-normal modes, so it's like an earthquake, right? So this is, I mean, perturbations on, again, depends on which kind of perturbation. So if they are driven by buoyancy, that would be a different perturbation. If they are driven by space-time modes, that would be a different kind. So I think we have to look at which phenomena is related
like
with
the
that.
way the glitches can be detected through time.
Yeah, for example, glitches, yeah.
Would you expect these stuff to be detectable at a detectable level from the timing? Even if the radiation doesn't change, let's say.
Okay.
I was just trying to see what order of magnitude effect these are.
Yeah. Okay, I'll have to think about it, but I don't think it can be, I mean, that obvious for a detection in a radio, but I'll think about it as well, yeah. Yeah, sure.
Okay, I think we'll have to close. I'm sorry if people had questions. You can carry on during the break. We have run out of time. So let's thank all the speakers of this session.
So we have a couple of announcements. So the next, the last session of KD Abhayankar Best Thesis Presentation Award and the general body meeting will be happening here in the auditorium. Okay. And the parallel session, Sun and Solar System 2, will be happening in L04. So the KD Abhayankar Best Thesis Presentation Award and the general body meeting will be happening in the auditorium. And the parallel session, Sun and Solar System 2, will be happening in L04. Thank you.
Something was really wrong with the
computers.
My answer was so I don't know why. It's always so frustrating. Everything runs smooth, it always runs smooth.
No, no, just a lip. Wait, take off. Hello, 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 hello. ठीक है, this is sounding good.
Hello.
So good morning and welcome back to this session. And we are running a bit late, but let's see. I hope we keep to the time. So this session, this plenary session, is about the activities of the Astronomical Society of India. We have two presentations. The first is regarding the public outreach and education activities from the POEC. And the second is for the gender equity activities. So I now invite Professor Dibyendu Nandi to give the report about the public outreach and education activities that they have been doing.
this? This is off, right? Otherwise, there'll be. It's off. It's off. Okay. All right. Good afternoon, and welcome to this session on activities of the committees of the Astronomical Society of India. This is going to be a slightly different talk from what you've been used to. What I am going to cover is the activities of the Public Outreach and Education Committee of India. I'll highlight what we have done over the past 1 year and what is our vision moving forward. Let me begin with a brief history of the Public Outreach and Education Committee. So this was constituted in the year 2014 at the ASI meeting in Aizawl, Mohali. So the first committee that was constituted was led by Ratnashri, whom many of you know. The mandate of this committee was to highlight and showcase Indian astronomical facilities, the research that is going on in India, important discoveries to the public, conduct training workshops for students and teachers, liaison with the media to ensure that the work that we are doing is getting out in the public domain. We are also involved in putting up astronomical education resources on the web, which can be accessible to students and teachers, and our website has more details about this. The overall idea is to ignite a passion for astronomy amongst the general populace. And of course, one can ask if there is any tangible benefit for it. My feeling, and I think the feeling that the EC had when we initiated this, that there are tangible benefits which will come over a course of years when we are effectively being able to advocate for the science that we do to the public, to the taxpayers who fund our science, and the government. I'm really an odd person out here because I am following some real stalwarts in the field of astronomy outreach. The first chairperson of this committee was Ratnasri Dandivada. The second was Neeraj Mohan Ramanujam. He was followed by Aniket Sule. I do not know why ASI dumped this work on me. I think it would be appropriate here to take a pause and acknowledge the contributions of Ratnashri to popularization of astronomy in the country. This is the last time I met her in 2018 at I think the IU Symposium on long-term solar activity in Jaipur. Here she is pointing out to the sun and talking to the public. Then the pandemic hit and we lost her in 2021. The Wire India for her obituary wrote that every community has a few people who are so central to its functioning, so exemplify its purpose, and so looked up to that it seems impossible to contemplate a future without them. Ratnashri, who passed away on May 9, 2021, was one such person in the astronomy community of India. She was the director of the Nehru Planetarium in New Delhi, which is under the Nehru Memorial Museum and Library for the last 21 years, and was a bridge between astronomy research and the people. I will quote here Rabindranath Tagore. I'm a Bengali. If you cry because the sun has gone out of your life, your tears will prevent you from seeing the stars. So we continue the work she began at the ASI POEC. And what I'll do is I'll highlight to you sequentially the work that we have done over the recent past, starting with my first assignment, which was being the booth manager for the International Astronomical Union activities of the Astronomical Society of India, where we had a booth for the first time. I'll also highlight our activities at the Young Astronomers Meet held in Aries, at the National Space Science Exhibition held in Kolkata, as well the Moon Festival. We don't have a report yet, but it's just concluded in Tamil Nadu, where we did outreach in the regional language. We're also involved in the International Astronomical Union Name an Exoplanet, ExoWorlds contest. We are having quite a bit of outreach at this ASI meeting, which I'll briefly talk about. Also, our activities in training students and teachers through various organizations like the HBCSE and the recently instituted IU Office for Education. Well, so let me tell you a little bit of a history about this, because this is significant and many of you don't know about this except those who attend the IU and those who are at the ASI EC. So in our history since independence and in the entire history of the Astronomical Society of India, we never had an Indian booth or an Indian presence in the IU exhibition, which if any of you have attended the IU meeting is just a brilliant thing, which is a place where people conglomerate, the poster sessions are there, and various organizations, various countries showcase their astronomy activities, facilities, highlight their work in the IUGA. This is something that was inspired by, I believe, a conversation between Aniket Sule, Ajit Kembhavi, and perhaps Surud and Yogesh Wadekar. Somewhere, I think, in Vienna in 2018, I guess, right? And the EC approved it, and then a team was put together who worked over a sustained period of years to put together material, which was then exhibited in this first booth of the Indian astronomy community at the IU. What you see here is a picture from the opening ceremony. As you can see that we did have quite an amount of footfall and a crowd. This is Aniket here explaining the posters to the IU president, Deborah Elbrin, as well as the chair of the Korean National Organizing Committee and the general secretary of the IU. We also, what we did was we presented some mementos to commemorate this event. We declared an India Day at the IU. On India Day, we all dressed up in Indian clothes. We invited the IU president. And on behalf of the Indian astronomy community, we presented a statue of Nataraja, as well as a plaque which contains, I'll get to it, which was presented to the IU president as well as the chairperson of the National Organizing Committee. I'm forgetting her name, I think Kung Suk Ho or something. Later, Deborah Elmgren wrote to me saying how deeply she appreciated the Indian presence and what he did there, and that the statue of the Nataraja as well as the plaque are going to become permanent exhibits at the headquarters of the IU at Paris. This is the plaque which was presented to the IU. It has, of course, this beautiful picture from Dorje Angchuk from Hanle. What you see here is the Himalayan Chandra telescope, and I believe also the Growth telescope, and the Milky Way. On the left top, you have an image of the Witch's Broom Galaxy nebula from the Astrosat mission, and on the bottom left, you of course have the antennas of the Giant Meteorology Telescope. We conduct a couple of different events. The reason I want to talk about it is because I want to talk about how outreach has evolved and what others have been doing and what we could do in principle. So we also conducted what we call the Great Indian Raffle on one of the days, where we had quizzes on different, well-known Indian astronomical facilities, important contributions to astronomy by astrophysicists and astronomers from India, and about locations of Indian astronomical facilities and its geography. And we had prizes to give up, which included, you see Divya here actually conducting the raffle. We had prizes which consisted of Indian handicrafts from all over India, and of course fine Darjeeling tea from Kolkata. The icing on the cake was that 4 of our students actually won the IU PhD prize, which had been postponed over the last couple of years because of the pandemic. So 4 of them got it together in this IU. So this is really nice in the sense that we really made our presence felt, And the sense of community that we had there because of the booth is something that I experienced for the first time in any IU. And I believe this is something that we should really repeat. What did we take away from the IU? And this is important for the EC if you want to repeat it. The India Day and the raffle were great crowd pullers. If you just give a booth and stand there with posters, some people will stop by, not everybody. You have to do events which involves the whole community and gets them to you. This is something important. We like to make brochures talking about all the stuff that we have done. Nobody likes that. It's good for your ego, what they like. And this is what we found out, because this other rich countries and organizations had stuff to give away like USB drives, mugs, scarves, and things like that. So we have to, if you want to really attract people and you want them to take away something which they would keep them with themselves, it has to be useful gifts, which can have your logo, which can have logos of Indian facilities, of the ASI, of different organizations, but they don't like brochures to take away. They like real useful stuff. We also had some issues with volunteers because there's not a big crowd of students or postdocs or faculty at the IU. So many of us were stuck there full time, and I don't know whether Asmita is here. Asmita is the person who was really stuck there full time helping us, because many of us were scuttling between the science sessions and the booth. So this is something to keep in mind, that many other booths had dedicated outreach personnel, paid personnel, who are there throughout. This is something that we should think about in the future, unless we have a big community of people going in where we can rotate volunteers. It has been recommended from our side to the EC that we should have a traveling set of posters, which will be evolved out of the posters that were there at the IU. We will update that every year. And we would like to hit all the major international conferences as well as the national conferences with this traveling exhibit. That I'm very thankful that people who came before me, led by Aniket and others, actually designed. The Young Astronomers Meet was held, I believe, in November in Aries. I was not physically there, although I gave a lecture remotely. The goal was to, from the outreach perspective, was to do outreach for the local schools, and this is something that we really do. Wherever we have an event, we like to reach out to the local region. We wanted to familiarize the young astronomers in attendance, mostly students, with the activities of the Outreach and Education Committee, and encourage them to join us. And I will tell you the fruits of this in a little while. You will see an evidence of how one group has now come up and doing really well. So this was initiated by the Outreach Committee. It is coordinated by Aries and Virendra, who's my deputy at Aries, and it was also designed by the IUCA outreach team. So multiple organizations were actually involved in this. Schools close to Aries were approached, and finally a set of schools were determined where outreach can be done. And really young students were targeted for this outreach, and this was a big success. Multiple teams helped in this, and I'm thankful that the YUM, which is the Young Astronomers Meet Scientific Organizing Committee, the Aries LOC, and the POC and the IUCA SciPub committees worked together to deliver this. Here are images from the outreach events, which reached more than 1,000 students in different schools. We had involvement from more than 15 research scholars in these outreach activities. And we do recommend the continuation of these activities at every year. This is a beautiful little painting on the right bottom by, I think, a little kid who says, "Thank you, Aries, for doing this." And this is why I think there is some question about whether we should really be divided when we are attending ASI meeting and be doing outreach while the ASI meeting is going on. I differ here with the EC. I think we should be doing this. Because you want to make the presence of the astronomy community felt wherever you are having a big event. This is important, not just from the perspective of taking astronomy out, but also from the perspective of the institution. In this case, IIT Indore, which has invested so much in hosting these events. And I think this is important for all future organizations which are going to bid for the ASI events. Well, the next big event was the National Space Science Exhibition. And it turns out ISRO does this every 2 years, but it never really had an outreach component to it or an exhibition component to it. And then we got the responsibility of hosting it in Kolkata last year, and we decided to have an outreach component for it. In partnership with multiple Kolkata-based universities and colleges, we organized an exhibition at Science City over 4 days, which was entirely managed by student volunteers from CCI Kolkata, and saw participation from multiple astronomy institutions, ISRO centers, universities, and also private industry partners. And ASI also had a dedicated booth in this, and ASI POEC members were out there volunteering, doing solar viewing and other stuff. What was the goal here? The goal was to bridge the astronomy community and the space science community. ASI does not have a presence in a big way at the NSSC. Neither is the reverse true. ISRO does not have a presence. I see Sita sitting here. I don't know whether Girish is here. I saw him yesterday. I would like ISRO to also get seriously involved with the ASI in terms of outreach and host a ISRO stall, come out with his team, and do outreach with us during the ASI meetings. I think these two communities which work together in some ways in delivering science, but orthogonally in delivering outreach, have also got to come together for making a big impact. These are images from the NSSC. We had footfall of more than 10,000 over a course of 4 days, multiple visits, organized visits by schools. We had 3 hours of coverage given to us by Prasar Bharati in DD Bangla. We do hope that ISRO will continue with this tradition of having outreach events and exhibitions in its future meetings. This is the exhibition space. We took a big hall out, and there were 19 different booths out there. This is a lecture by Kiran Kumar at Calcutta University. This one is a Women in Astronomy panel, Space Sciences panel, which was held by BITM. All part of the NSSC. We really took this out to multiple venues across the city for a bigger impact. This is important. We had about 5 different industry partners who came in, and we had 2 different industry booths. One where many of these industry folks conglomerate together, and a separate one. This is something that I think ASI should take a leaf out from, because this is also important in the perspective of funding and building grassroots connections with the industry. Of course, it's easier to get them to a space science exhibition, but I think if you work a little bit, it will not be too difficult to get them to the ASI meetings as well. We also had a Bengali science adda out in the open here in the evening, and we do hope that we'll be doing something similar in Hindi on, well, Saturdays. Tomorrow, time is flying, in Indore city when the POEC is going to the city tomorrow. We also worked with the International Astronomical Union to host the Name an Exoverse contest, where the idea was different national teams would propose a name for an exoplanet and its host star. And every country had a designated organization. For India, it was POEC to select an entry and send it out to the IU. Samir Durde was put in charge for coordinating this, and many ASI POEC associates. Many of us were involved in judging this. I will not be able to disclose anything else at this point in time, but the names have been selected and are out with the IU, who will make the final selection. We just recommended the names. The Moon Festival, which just concluded in Tamil Nadu, is an example of large-scale outreach in the vernacular language, in the local language. This happened over a course of 3 days all across Tamil Nadu. They approached us for facilitating this, and we designated TVV, who is somewhere here, as the POEC coordinator to liaise off with this event, and Neeraj, Varuni, and others who are also POEC associates help put this event together, which here also was a grand success. What are we doing at the ASI meeting? Well, we have already concluded our rural school visit, where we had a solar watching, night sky watching. We had lectures and interactions with the students. We're going to IIT, so we are in IIT Indore, and we have been conducting, I don't know if you've seen, solar viewing sessions, 10 or 5? 10 minutes, okay, good. We are also doing solar viewing and night sky watching sessions in IIT Indore, and we're hitting IIT Indore City tomorrow, where a full team of the POAC is going along with student volunteers, where we're taking the outreach out to the students and the public. We have selected a particular venue, where we are going to have astronomy themed art competition. We are going to have sky watching session, basically solar because it's a daytime event, and we're also going to have outreach lectures and interactions and maybe some adda in Hindi. I'm grateful for support, strong support, in fact, without which this should not have happened, from Mononita, who was designated as the LOC liaison to the POAC, who and her team from the Department of Astrophysics, Astronomy and Space Sciences at IIT Indore has been instrumental in delivering this local outreach with us. It has been, it's been pretty stressful for them because it's a small team and they're helping out with the organization for LOC as well, and us. I'm also grateful to Alok, who came down, who's from the Aryabhat Foundation, who came down from Bhopal and is with us and really playing an important role here. The poor guy came up with fever. He's been working too hard last night. The Cosmic Varta team who are here, who's helping us, as well as student volunteers from different institutions around the nation. We also do astronomy education in terms of student and teachers training, and we have the Homi Bhabha Center for Science Education, which is playing a big role, led by Aniket and his team. So it does training for the Astronomy Olympiad for students. I don't know whether some of you are aware, we have 2 young and upcoming upstarts, astronomy faculty, who actually are alumni, as kids, they're alumni from, from this Astronomy Olympiad. I think Varun Vallarao is one of them, and Shrihars Tendulkar, right? Yeah. It also organizes teachers training workshop throughout the year. In fact, they recently concluded one in IIT Indore. I know they did one in ISA Kolkata, and they have been also doing this in HBCSE for a long time as well. So these activities are coordinated by Aniket Sule, and many astronomers from around the country do help them in delivering this. Well, these are pictures from the Astronomy Olympiad and as well as their team at NIUS. Well, let me talk a little bit about the evolving landscape here, where we're headed, and about the new initiative that's coming up. One of them is the IU Office of Astronomy Education at IUCA, which is a big thing that has happened to us. The other thing is Cosmos project at Mysuru, which the Indian Institute of Astrophysics is leading. Also, the Students Run Outreach Group Cosmic Varta, which has been doing fantastic work over the last couple of years. So the IU Office of Astronomy Education, which was constituted over the last couple of years, is led by Surhut with Aniket, and they have Asmita as well as Moupia. Small group of people, but they're doing some important work in terms of global leadership, in terms of defining the role of astronomy education around the world, coordinating activities for the IU in India and, around the world, as well as with a strong regional focus in terms of teacher and students training, curriculum development in various Indian languages, translation of astronomy resources from around the world into Indian languages. And I would encourage anyone when they approach you to do, lend them a helping hand, because again, it's a very small team doing this, and I would really like this to succeed and grow in India. The Cosmos project at Mysuru, the Cosmology Education and Research Training Center, is an upcoming state-of-the-art planetarium which is being constructed at Mysuru, which is being overseen by the Indian Institute of Astrophysics. This is essentially going to be a planetarium which is also going to host students' training and education programs, of course, as a planetarium for the public. This is being supported by multiple Indian organizations, including the Office of the Principal Scientific Advisor to the Prime Minister and the Office of the Finance Minister, And I'm looking forward to see this grow because I love Mysore as a city. So they have multiple activities which are planned there, and they've started some of these activities, which includes tutorials, demos, and translation of manuscripts. And I believe they are already translating about 24 manuscripts. Okay, Cosmic Varta is another, so 5 minutes, right? Yeah. So Cosmic Varta is another organization which has recently started. I'm not going to go through the details of this, but they're a student-run outreach organization which is also delivering outreach across the country, associating themselves with various events like ours. They're going to help us tomorrow with the art competition. Lakshita is here, Vishal couldn't make it, Sridharan is here. If you want to volunteer for them, please get in touch with them. I think this is a really nice initiative. What is our future vision? Well, when I took up, I really wanted to see what else can I add beyond what is going on. Couple of things we've already implemented, which is the Women in Astronomy lecture series, and we'll hear more about this soon. The Astronomers in Residence program is something which is to support the growth of astronomy in state and private universities which do not have astronomy groups, where you want to send out astronomy faculty for a couple of weeks over a course of 1 year by rotation to various institutions. We want to have a dedicated meeting for astronomy education. This is a proposal coming from our groups which are involved in education. We want to evolve YAM to assimilate postdoctoral fellows looking for jobs and career counseling, and there have been a couple of people here who have been looking for jobs. Right now, there are job advertisements from ARIES for outreach personnel, there are job advertisements from the Homi Bhabha Center for Science Education, from the Indian Institute of Astrophysics. So get in touch with us, we'll put you in touch with them. If you're looking for outreach jobs, they're there. We are also constituting a recommended to the EC, and I hear today morning the news that one of them has been approved, the Journalism Award for Sustained High Quality Reporting in Astronomy. Why is this important? This is important because you also want to motivate and inspire the media to report on astronomy. And this is a sort of a positive way of catalyzing sort of a nice competition in the media houses to ensure that they get into coverage of astronomy in a big way. We also want to cultivate industry academia relations from the grassroots level, not in an ad hoc level. And this is something that we'll be talking to the EC over the next couple of months. What are the challenges that you have? Well, I'm not going to spend too much time on it. I'll just leave you with these questions because we're still thinking about it. So right now, the government has basically mandated that every institution has their own outreach teams. And so whereas 10 years before, ASI POEC was pretty much the only game in town doing outreach, now multiple other organizations are doing it. What is our role in this changing landscape is something to think about. We are stretched. We need more volunteers for our activities. I've been watching who's doing what. I think now we are ready to expand the association program to beyond what we have to incorporate more people. Finally, times are changing, and there are sensitivities that we must be aware of. Astronomy is open, is something that the society is deeply ingrained in. It's useful for us, it's easy for us in a way, it's also difficult because we have to work with traditional beliefs on the one hand, we stick to the to our methods of scientific logic and reasoning, and how do you strike this balance without distancing people away who really are the people the people you want to reach out to. This is the challenge we have to also worry about thinking forward. I want to end with what do we do this? Why do we do what do we do, right? Well, so astronomy is one of the most ancient of all sciences. I mean, you just get out there, it's in front of you. You can't ignore it. You're the sun in the daytime, the sun sets, and the stars out there, and we marvel at the universe. Carl Sagan said that astronomy is a humbling and a character-building experience. People like Galileo and Giordano Bruno has also found out it's a dangerous experience, right? But it's something that we work, that is our work, something that we love to do also. And we'll be failing in our duty if we cannot carry that love to the people who are funding our sciences. The tangible benefits to it for the students, I think it's very important because it teaches you how to communicate, how to present your work better, how to write your research papers better. There are intangible benefits, like this happiness that you get. I purposely blurred their faces. 86-year-old man who read about the National Science Exhibition in a Bengali newspaper, came with her niece from Malda, which is about 300 kilometers north of Calcutta, to experience it. This is what you get at the end of this, which is much bigger than the papers and the citations that you have, which is what I realize now, really. I guess most of you worry about this anyway. I'll end here, and I'll invite Arunima to do a present duty for us. Arunima, are you here? We have this citation for the first Women in Astronomy lecture series, and I'd request Sita to come up on stage to receive this citation from the POEC and the working group on gender equity together. Arunima, come up. We had certain other things, which was, can you please get them? This is a citation for Sita, which, well, you can present. Thank you. Well, the flowers I will present. Okay. This you should hold.
Sure. Thank you.
There you go. No, not this, the other one, the glass one. This is for somebody else. The heavy one. Well, that's why I said you should have kept it here, because I like to have control on this. Okay, thank you. Okay. Yeah, this is something that Sita is going to love, because, well, I need to show it to you.
Oh, wow.
There you are. I think everybody should say this. This is Sita's favorite satellite, AstroSat. I think NGC something, a spiral galaxy inlaid on this. Hey, come here so that you can take it. Urudima, come here. Come. Okay. There you go. Thank you, Sita. Very grateful to you for delivering the first lecture. I'm not finished. Sorry, Sarita, I'm keeping you waiting. Can I have the other two stuff, please? Mononita, can you please come up here on stage? This is surprise, which is the chairperson's discretionary stuff. On behalf of the astronomy community, we would like you to, if Mononita is not there, is she there? Please come up here. This plaque, I don't know if you can see it. This is again an image by Dorje. I request you to accept it on behalf of the astronomy community for all the hard work that you put in, and maybe perhaps either keep it at Dasi or give it to your director. That's your choice that you make. Come here, don't hide. There you are. Thank you. Finally, there is one guy who's out here. Munita, you need to take this as well. That'll be because the stand is here. Alok Mandavgane from the Aryabhat Foundation, are you here? Alok? This guy is an example for everybody here. He did his MTech from IIT Delhi, did an internship at Microsoft, got the bug for astronomy outreach, left everything, and is full-time doing astronomy outreach, building apps and making money out of it. He's also been an enormous help for us in doing the local outreach, not just here. He also designed the Zero Saturday app constituted by the ASI. He's been working so hard that he came down with fever yesterday. But on behalf of the astronomy community, you as well. Come here.
Thank you. Thank you very much.
Thank you. Okay, I'm done. I have nothing more to give. Thank you. And sorry, Sarita, for taking a bit more of the time.
Thank you, Dipyendu. Yes, we are running a bit short on time. So thank you for showcasing the activities that POEC is doing. I don't know if we have time, but if anybody has a comment, maybe we can take that quickly.
This is for you.
I don't see any hands raised. So we'll move on to the next set of activities. I think this is by the Working Group of Gender Equity, and they are, in this, Arunima will be making a short presentation followed by a panel discussion. So, Arunima, yeah, 30 minutes.
Yes.
I'll give you a reminder.
Yeah, good afternoon. So as you know, we have planned for a panel discussion in this session. Personal observations of gender equity related to gender equity in academics. And while I flash a slide on the activities of the WGGE, the Working Group for Gender Equity of the Astronomical Society of India, I call on the stage the panel members. Nilanjana Nandi, ISER Tirupati, Janhavi Baghel, NCRA, Arijit Sir, Presidency University. Yeah, please be seated. Dr. Nayana AJ, IIA, and Professor Moushumi Das, IIA. Light down করে দিতে বলো, ওরা আসবে পোডিয়ামে।
ঠিক আছে, এটা ঠিক আছে?
না না না, অন্যটা। Thank you. I now request the panelists to begin the panel discussion. The floor will be open for questions and comments after all the panelists have spoken.
Hello and good afternoon everyone. I am Nilanjana Nandi from ISER Tirupati. I thank ASI WGG for giving me this opportunity to share some of my personal experiences and observations regarding gender inequalities, and that can be related to the reason why we see lesser number of women in science and research. And I guess many of us sitting here in this auditorium can relate to at least one of these points. So it starts at a very early age when girls complete their 10 plus, and they are at a point where they have to choose for specialization for 10 plus 2. It is widely believed that women are more suitable for arts than science. And the immediate responses we receive are that, can we do it? Or should we give it a second thought? Because there's no coming back from that point. Afterwards, when we continue with science, another judgment revolves around us that women are not capable enough of grasping concepts, or they are not capable enough of giving enough efforts in understanding concepts, or like brain work or imagination. So when it comes to tests and examinations, we are doing good because we are good at memorization. Probably that notion leads to the assumption that mainly biology and chemistry are for women and maths and physics are for men. Probably people don't know, and they are not aware of the fact that how complex these subjects are, like biology and chemistry are, but still this notion has kept itself alive. Several of us completely ignore all such things and we complete our bachelor's and master's. Then again we face few questions that have we enrolled for B.Ed or other qualifications that are nowadays necessary for getting a job of a school teacher, because we have to get married, we have to take care of our family and children. So it's being a school teacher is better because it's kind of a 9-to-5 job. So here we can see the extent of demotivation we face since our childhood, and the mental strength and enthusiasm keep decaying over time. And only few of us are strong enough or fortunate enough so that we get very supportive peers and family, so that we overcome all such views and comments, and we continue with a goal of being a professional scientist. Now, choosing science as a career is very time consuming, because it takes at least 8-9 years to complete PhD, postdoc, and to get a possible placement. So by that time we get pretty old, so we often get the recommendation, or we are asked that we should get married, we plan our family, then we should delve into the time consuming career plans. Because if we focus on career, then who are going to take care of the future or previous generation of our family? Also, living outside, away from home, alone, a girl, it's quite frowned upon by the society. So based upon my limited observations, I believe we are losing a good proportion of youth and talent. And since diversity is necessary for the enrichment of science, we are probably losing out multiple perspectives of a same scientific problem. So this is all I wanted to share today regarding gender inequality. Thank you.
So, good afternoon, everyone. I am Janvi Baghel from NCRA, and I'd like to thank ASI WGGS group for giving me an opportunity to share some of my personal experiences and general observations that I've had in academia about this gender equity issues and what kind of things we face. So, as we already heard, that it starts very young, but one of the most important things, the first point I'd like to touch on, is we don't see examples to aspire to as much as we should. The number of students, the fraction of students who are PhD students, who are women, is around like 30%. So women are enthusiastic to enter into academia, but by the time we see like, okay, how many women are getting faculty jobs, it's almost 10%. So we are losing women somewhere in the middle. That is coming because of the lack of support. So it almost becomes like either you have to leave all other worldly things and just become an academic and leave everything behind if you want to have a career in academia, or you can have your life and academia together. That is not possible if you're a woman. So that is one of the things that I have observed, and I have even seen. There is a pressure to, okay, if you want to have your rest of your life apart from academia and also academia, you can't really do that. So that is one of the things, one of the points that I wanted to touch on. We don't see these women who are faculty members, who are like doing research, who we can aspire to, who can achieve it all, basically. And second point that I wanted to touch on, because there's this huge gap in the number of women that are there in academia, there's also this thing of so-called boys club culture that I have seen from like very young, and even now, if there is a social event and some people are going, oftentimes you get left behind because women are so less in number. Nobody thinks to ask you, and often things over there are discussed and information is there, that there is a delay of information reaching you, that you should have applied for so and so exam, or you should have applied for so and so grant. That delay leads to a lot of loss of opportunities, because often you get to know them quite late. So that, I think, is a experience that I have seen quite commonly, and I've known quite commonly as a woman in academia, that you get to know about opportunities and things after the time has passed, because of this information lag, because of this so-called guys club culture, that you don't really get to get that information outright. And the third thing that I have seen is a very dual kind of thing of nature, that even if you work despite all of the shortcomings, even if you work really hard and have like a good academic record, you have multiple papers, multiple everything, your work is still undervalued, it is still diminished, and you are scrutinized way more than your male counterparts in your research in any level of academia. And that leads to like a dual thing, in the sense ki you will still get to hear ki, oh, you got this and this because you were a woman, but at the same time you are also like the value of your work is counted at less because you are a woman. So these were a few of the experiences and a few of the points I think many of us can relate to when it comes to being a woman in academia, and what kind of discrimination, a very low level, things have improved over the past, but there are still a lot of ways to go when it comes to this kind of insidious small ways of discrimination that's there. So thank you.
Hello everyone, I am Arijit. I am coming from Presidency University. First of all, I would like to thank the WGGE and ASI for giving me this opportunity to speak here. So, I mean, there are, like Janhavi and Nilanjana mentioned, there are some unique challenges that female students face in academia. I cannot directly relate to them, but what I can say from being in academia for 5-6 years, what I've seen. So, if we begin during my bachelor's time, so from my bachelor's time to the master's time, so I came across around 60 classmates. Out of those 60 classmates, only about 10 were female students. So and this is a Presidency University. This is Presidency University, which is a very well-known public state-funded university. And the thing is that Presidency University, out of the total 2,000 students, more than 50% are women. But when you are coming to, when you are coming to the sciences, that is this equity is completely gone, and that is very disheartening. And what happened was that over this course of 5 years, what I saw, around 14-15 people actually went into some kind of PhD program or something. These people might take up a role in science and academia in future. Out of those 14-15 people, precisely one woman got into a PhD. And that is there is of course something going on which is very much unaccounted for. And this is, I personally believe, because this has to do with, there has been a lot of talk, like Janhavi mentioned, that MSc and BSc students are not getting the opportunities to join the PhD. The number falls from 30% to 10%. That is definitely a very significant thing. But there is another point that Nilanjana raised, that during your high school years, when you are going to take up a career, thinking of joining some college, taking up some discipline, studying some discipline, that point is where we should be focusing on. And we need strong role models, because visibility matters. If young women are not seeing that there are young researchers like Nilanjana, Janhavi and others who are barely a few years older than them, who are doing incredible work, publishing in international journals and leading astronomy in India, this needs to go out to them, and not just to them, to their parents. I don't know how this can be done, but this is my suggestion, that this needs to be done. Because then maybe we can, this gendered binary, that arts for girls, science for boys, that thing can be overcome. So that is the thing I wanted to speak to you about. Thank you very much.
Hi everyone. First of all, I would like to thank ASI and WGG for giving me this opportunity to share my personal experience as well as some observations in terms of gender equity in academia. So I agree with all the points that my previous speakers mentioned, and I would like to share a few of my experience on a particular phase of the life which for example Neelanjana or Janvi mentioned, is about the phase when we are actually deciding to have a family or have a kid, how difficult it actually is. I had my baby soon after I submitted my thesis, and now she is 3 years old. So I became pregnant in the final year of my PhD, and I had to figure out and understand a lot of things during the last 3 years to be here in academia, and at the same time to be a mom who can give whatever the kid wants in terms of emotional support, taking care of the family, the kid, etc. So I would like to mention about 3 main points. So one thing is, it's a very, very tough phase of your life, and it is important to hold on. I have felt and have gone through the phase where I was feeling like giving up. I was feeling that I cannot make it and I'm not going to make it. But I had Poonam in my life as a role model, and I always look up to her, and now I look up to her even more because she has 2 kids and a killing career. And I wrote to Poonam like when my baby was like 3 months and COVID hit, and there was absolutely no help in terms of anything. I told her that I am not able to manage, I have to resign or I have to stop. And she actually took time to call me and hear every single thing which I wanted to tell, and I could feel that she is the person who understood me completely. And the comments or the suggestions which she gave me, I decided to hold on. She said that it's okay, this is a phase you are going through, but it's going to get over. The kid is going to become older and you will be able to do or invest more time to research. I did that, and that's the first thing which I want to tell the people who would go through the similar phase, is that don't give up, hold on. And the second thing is, we do have 6 months maternity break, but that 6 months is nothing compared to the time scale for a child care. In 6 months, the child is not going to be on his own or her own. You are going to end up spending more time. The child will fall sick every other week when they go to play school, or there are so many things which you have to invest in. So be ready to take help. So there is this social thing which people say that, oh, how can you leave your kid in a crush or in a daycare? How can you do that? So there is nothing wrong in taking help, being a working mom. You find out the right place, the right people, take help in terms of doing the household or in taking care of the kid, and you will be able to do your work and slowly get back. And that is the third point which I want to make: get back to work after 6 months. Don't fall in that huge potential well of taking care of everything. You will just be there. So it's important to get back slowly. There is a pace. You will start doing things slowly, but you will eventually get back to there. So that at that point, there is a point 4 where you really need help and people who are considerate about or sensitive about all these issues. For example, you would certainly need flexible working hours. You can't always be 9 to 5 in the office, or you can't always attend a meeting which starts at 9:30. So it's important to have either as policies or by being considerate in work environment to give that space and flexibility for working moms. which will make a lot of difference in terms of their productivity as well as improve the quality of the environment, and it will certainly make sure that more women will be in the community in all higher up positions. And in that sense, it's very important to have people who are role models, who are part of policy makers, who are there to make decisions on all these aspects. So I would stop there. Thank you.
Hi. So I think before me, all the speakers have really described all the problems that they're facing. So what I'm going to do, because I'm much older than all of them, I'm going to give everyone a historical perspective. And first of all, before I start, I don't think I need to thank anybody, because I think it's due for people to listen to me. I think it's long overdue. And I have a book because I have to remind myself for things to say. So though I'm stopping you from going for lunch, please bear with me. So let me start with the good news. The good news is, I think in the last 2 decades, things have improved. When I was a postdoc, when I was, looking for jobs, people told me something really outrageous. They said, your husband has a job, so why do you want to work? You work for free, do research for free. And I'm very glad to say that people don't say that anymore to women looking for jobs. So that, I think, is a real positive improvement. I think there's also a somewhat relaxation on the age criterion. People are more understanding about the age thing, although I think maybe the IITs and ICERs and maybe the central universities need not put that 35 age limit on their forms. That should be removed, especially for women, but even for men. So that's the second thing. Now, though these are good points, these are good things, and now people are also noting numbers, how many women are there in the meetings, in the speakers, so that's all great. But we still have a lot of issues. The first issue is, of course, as the people here in the panelists said, there is a leaky bucket. So when I take interviews, I'm part of interviews where we're interviewing students, sometimes all the PhD students are women. But when I look at the faculty, there is obviously some huge leaky bucket there. And that's because when a woman nears the end of PhD, the question of marriage, or simply, get your PhD and disappear. This is the attitude of most people. So that attitude has to drop. It's not completely gone. So the leaky bucket is definitely there. That has to go. The second thing is that there is, of course, as you just heard, a difficult time when a woman marries and when a woman has children. So some amount of credit has to be given there. We still have to have a certain amount of, error bar for women who have taken up this step. So those things are not there. But there's also a lot of subtle negativity towards women that I have noticed in meetings. And many people have told me that. There is aggression towards women speakers. If they do get a talk, there's still aggression often towards them. There is, they're not often given their credit. For example, they may be the PI of a very prestigious paper, but they won't be asked to give a talk about that paper. Even they are the person. She is the person who has led the project. I've seen this with my own eyes. So that really disgusts me, that a woman is not given her due because of the gender. So that has to go. Now, a couple of other things that so we also have to have more understanding for women who face the two-body problem. Very often, if the man has a job, the woman is asked to adjust, or we say in Bangalore, adjust Mari, take up some small job somewhere, some project position. So we should discourage that. We should, if the people in the hiring positions should try to make sure that both, the talent of both the persons is not wasted. So the two-body problem is something that has to be addressed. And before I end, of course, there is the sexual harassment, the whole issue of sexual harassment, and that is still ongoing, and I still see it around me. It may not always be obvious also. It can be in simple remarks, or it can be in, biases against a woman. So these things have to go. Now, there are actually some good things that have come out. There are these schemes for women, women scientist schemes, but some of the things can be improved. For example, the Women in Science scheme, which is really, I think, a very good scheme, that should be increased. It shouldn't stop at the age of 50 or 55. It should go well into the 60s, because retirement age is 65 in the universities. So that is something that should be changed. There should be no age limit. This whole age limit, the ageism has to go. So there should not be any age limit in any form, because it does affect everybody. It affects women the most. And women who are taking a break due to any reason, due to family circumstances, or it may be a man who has become a caregiver, people taking a break in science should be given encouragement to continue. It shouldn't be like a penalty point against them. It shouldn't be held against them. So these are some of the things I think that should be done. I think I've covered it mostly. If anyone else has any more points, please raise your hand.
Yeah, thanks a lot to the panelists for sharing their insights. The floor is now open for questions, comments.
Yeah, thanks to Moshimi and all the panelists for highlighting the problems that are faced by women specifically in Indian society. I was rather alerted by the notion that Moshimi brought up the issue of harassment. I would like to point out that harassment is not specific from one gender to another. People within their own genders harass each other. It's a matter of power play, right? I do believe that the Equity Committee would do well to look into issues of harassment irrespective of where they come from, to establish within the ASI itself a framework for dealing with harassment, and to follow within ASI itself the framework and the rules laid out for dealing with harassment. And those rules need not be extraneous to something that the government policy already dictates. We have in place in the Government of India policies for dealing with harassment. The ASI can just follow that and deal with it strictly. That's all. Thank you.
Hi. I have a different view on the statistics related to BSc, MSc students. I'm from the south, I'm from Kerala, and I'm from a college wherein there is 75% of girls in BSc and MSc, which has been seen recently. So these days there are a lot of good number of girls coming into the science, even in PhD, people are doing postdocs, but as raised when it comes to the position of faculty, what is happening? So for a woman, there is a break happening always, and how good we are in accommodating that break. That is the point. So as a country or as a global community, how can we accommodate that break of a woman? So I've interacted with people internationally, they also face this. This is not the problem of our country alone, it's a problem with the whole world, I guess. So myself is a mother of two, I'm a fourth year PhD student, and I find research as a good career for a woman. Like, in fact, it's a very easy career for women, very relaxed, not relaxing, but enjoyable. So I had a lot of difficulties in coming out of the conditioning that we were enforced by the whole society, which we were pulled in. But I'm sure it will be easy for my daughter who is growing up. Like, for her it's easy because I am there, I was a model for her. So every woman and man out here who are breaking this conditioning, you are warriors, I would say. And this is what we can do. Like, communication helps a lot. All of you here speak to the young people, girls around you, even men. Speak to boys and girls, not only speak to girls, that's important. And this is a real change we can make, I believe. And we as a scientific community, how human people look at us. we are the superiors, but then still we are speaking about gender equity. I find it very contradictory. So that's
okay.
it.
Thanks for the comment. I think we are running short of time. One last question, Indulekha.
Just 2 points. One is regarding that information. We have dedicated sites which give you information regarding upcoming conferences. Like that, if we had a dedicated site for women, giving some general information regarding, like, for example, that the science
Women's
talent
science.
exam carries with it the obligation for submitting a project, for example. It will be nice. Why it's available, but if it is dedicated, more girls will know about it. Okay, there is a site, we can go and look at it. The other is a small point regarding Kerala and the larger number of women in colleges, etc. It comes about because parents are prepared to pay more money to send a boy to engineering for a professional course. So for arts and science courses, you will always find there are more women. So it's not an indicator. I mean, just adding to what is a student's perspective versus a teacher's perspective.
Yeah, I agree with that. Yeah, we are almost done. So before we disperse, I would like to acknowledge my co-committee members from the WGGE, Preeti Kharb, NCRA, Debarati Chatterjee, Ayuka, Suchetana Chatterjee, Presidency University, Aru Beri, Aizer Mohali, Mayuri Rao, RRI, Nirupam Rai, IISc, Ravinder Manial, IIA, and Sriharsh Tendulkar, TIFR. Thank you. Thanks for your attention.
Thank you, Arunima. We got to hear many different perspectives. Now I think we are really short of time. We are running half an hour behind time. It's 1:30 now, and the sessions were supposed to start at 2, but we can start at 2:20. So we need to go there and come back by 2:20 here into various parallel sessions. Yes, you have some announcement to make.
It's the same thing. Basically, the last session will be happening over here in this auditorium hall. Okay, and the sun and solar system is in L04. Thanks.
কালোটা হ্যাঁ, এটা